And we are going from the current slide here. I may even turn on the projector. So let me go over a few announcements. I think you've heard some of these before, others I know you probably haven't. Now, I haven't printed off all the ones I've seen on my email, because usually I'm checking email at someplace I don't have a printer. But one of these, I think I announced this before. This came from Mr. Jonathan Jefferson, who must be a coach here at Lawson. I don't know what he coaches, but that's what he has, Coach Jefferson at the bottom, Lawson State Community College. It's about a job offer from a company named No Kid Hungry. Have I told you all this one before? Yeah, I have. Okay, so I won't go through it all again. I've got the information here. All it has is a contact email address to contact Henry. Now, I don't know who Henry is, but the email address starts with HS and then 7 digits. So it must be Henry something another. Probably not something another, but something another. Okay. So you can certainly look at that. Now, this is just one of several of these. It's the only one I've got printed. But various universities apply for National Science Foundation grants to support summer research experiences for undergraduates. These are called REUs, okay? And UAB is one of those, and here's Ryan. Okay. And this one sounds like it could welcome people from a variety of majors, okay? The title of it, and by the way, the program will run from the 17th of May through the 24th of July. So I think that's about 10 weeks or so, okay? It's experimental and computational materials research. We offer a broad range of interdisciplinary materials research experiences to undergraduate students with diverse backgrounds in physics, chemistry, applied mathematics, and engineering. And it's not just limited there. When you hear some of the other things you do, you can tell there's even more stuff. The research projects include, but are not limited to, electronic materials, nanomaterials, lasers and optical materials, biosensors, biophysics, and biomaterials, and computer modeling. So there's a bunch of other things in there too, including computers. The scientific research projects are developed specifically for undergraduates by an interdisciplinary team consisting of science and engineering faculty at UAB. I've asked them to put up a poster down there somewhere in the hall near the student financial services office, that hall going that way toward the cafeteria. I hope they put it up. They said put it in a high traffic area, and that was one of the higher traffic areas. I knew they had bulletin boards. I have websites if you want to go see those. The application deadline is March 15th. That decisions will be made no later than April 15th. If students have any questions about logistics, housing, travel arrangements, they can contact Ms. Rita Cadenhead, our program coordinator. The phone number's here, the email's here. Now, the guy who's heading this up is from the Department of Physics. Like I said, broad range of things. When they mention logistics here, I think that means moolah, okay? They actually pay you to have a fantastic experience doing research, learning gobs of stuff, and they pay you for it. Now, that's a pretty good deal. They also pay you travel at least once to and from campus, not every weekend or every day, but to get there and to get home. And they pay you a stipend, I'm pretty sure. The details are not here, but they'd be at the website. Okay, so that's the external announcements. Here's one pretty major internal announcement. I've been asking this question for several weeks now. Are they going to open student course evaluations? And I understand that yesterday they finally opened it. Is that right? So you can now do your student course evaluations. And a student this morning asked me, how do I get to them? There's a couple of ways. They said, can I go through Blackboard? I'm pretty sure you can. I just can't tell you how to. Okay? I know you can go to the website and go through that way. But the easiest way, at least if they do it like they normally do, is they send an email yesterday, right? And in that email is a link, right? And if you click on the link, you go straight there. So the easiest way is to check your email. Find the one about student course evaluations, open it, find the link, click the link, you're there. And please do the student course evaluations. I'm a department chair, I'm a math department chair, and I use the student course evaluations more than any other single source when I'm doing my evaluations of my instructors, which I have to do once a year. So I use them. I think most of us instructors use them to see what students are thinking about, how we need to improve, things that we're weak in, that kind of stuff. I think just about everybody does that. But in addition to the courses, you'll also be asked to evaluate some other aspect, maybe the registration procedure, possibly the library, maybe food services, maybe groundskeeping, some other process here at the college. And you see, we as instructors, we get feedback from you every time we see you, whether you realize it or not. We read faces, we read body language, we read tops of head. No, nothing like that. But we get feedback, either one-on-one or overall group. A lot of those places don't get that direct feedback, and they really depend on your comments and evaluation there. So please help us all out and do your student course evaluations. Okay. Now, that's the school stuff. Let's now hit what we as a class are going to be doing. Today we're going to finish Chapter 6. We only have a few more slides to go. That includes, I think, only one more example to work and a few more slides, and we're through with Chapter 6. All right. Now, we then go straight to Chapter 8. We'll start Chapter 8, and we'll continue Chapter 8 ad nauseum. No, for quite a while. I'm going to shoot to get at least halfway through Chapter 8. If we get at least halfway through Chapter 8, maybe a little bit further, we may just end it early today. Because Thursday, all we have to do is finish Chapter 8 and do the test for Chapter 6. Okay? And that's all there is on Thursday. So that'll probably take a fair amount of time, but not probably the whole period. Okay?
Are we done with the labs?
No, we're done with labs for Chapter 6. We got one more lab for Chapter 8, but I want to cover the material before we do the lab. I think you want me to cover the material before we do the lab, too. So, yeah, we finished the third lab for Chapter 6, and that's all we had for Chapter 6. So, and by the way, that was our 11th lab, okay? We got one more for Chapter 8, and that'll be it for the term. So, today we'll finish Chapter 6, and hopefully get at least halfway through Chapter 8. Thursday, we'll finish Chapter 8 and have the test on Chapter 6. Okay? Then the following Tuesday, our last day of class, we will have the lab on Chapter 8 and then the test on Chapter 8. And, also, back up, time out. Tuesday also, I'll return every paper, every lab, every test to you on Tuesday, 1 week from today. Now, what does that mean? All your labs, all your tests need to be completed before class on Tuesday. Now, one guy came by today and wanted to make up some labs, but I had one student in the office, another one waiting. I said, as soon as I can get to you, I'll do that. I said, where do I meet you? He said, I'll be in the cafeteria. It took longer to get that student registered than I thought it would, and to do the grading for the one. He was doing late work. Oh, who would imagine a student would do late work? No. So finally got his stuff done, and then another student came in who had to register. I got her registered. Then I went to look for the student. I couldn't find them anywhere. Now I've been back again and still can't find him. And he's not here now, so I don't know what happened to him. But he did say he would get in touch with one of you two about the lab. So it's Mendez.
We have no way of contacting him.
Yeah. So I figured he must have a way of contacting you. I don't know. So anyway, so he was trying, but we've still got another week for him to get that caught up. Okay? So please get caught up. Now, what does that include? Research papers. Now, this class is pretty good. 1, 2, 3, 4, 5 out of, 13? Not great, but better than some classes. So getting research papers in, that means quite a few of you don't have it in. Please try to get your research papers in. And then the other thing, get all the labs and the tests caught up. Okay. Because on Tuesday, 1 week from today, I'll be returning. I can't return the research papers because they periodically ask for samples of student writing, so I have to hang on to those. But the others, I will be returning to you next Tuesday. If they're not in by next Tuesday, that's a 0. Okay, so please get them in. I'm thinking I'll probably drop your 2 lowest lab scores and, of course, your 1 lowest test score, okay, of your regular test. Okay. So Tuesday will be returning all the papers to you, and that's going to take a while, unfortunately, and then doing the lab for Chapter 8, and then having the test in Chapter 8. And that's all we got for Tuesday. Now, I have said, and I still will honor it, if any of you need to or want to take the final exam on Tuesday as well, it will be ready. But technically, the final exam is Thursday, and technically it's at 3 o'clock rather than 3:15. I'll be here all day, okay, so you got plenty of time to do that test. And it's going to be fairly short, so it's not going to be a lot. Now, there's only 6 people here, but let me just get a feeling. Are any of you thinking you will take the final exam on Tuesday or Thursday? What's your feeling? Tuesday? Okay. So then, in addition to everything else I said, let's figure to have pizza on Tuesday. So is that okay, or would you rather not waste any time with it? Okay. So Thursday, remind me to find out what kinds, that type of stuff, how many we should get. We'll talk about that on Thursday. Okay, so we'll have pizza while I'm returning the papers to you. Y'all can be eating pizza. And then once we get that done, this is next Tuesday, we'll do the lab for Chapter 8, then do the test for Chapter 8, and then any who choose to can do the final for Chapter 8. That will be Tuesday. Thursday, then, anyone who has not completed the final, I'll be here all day long on Thursday, so you can come in anytime, technically 3 o'clock, but I'll be here at 3, I'll be here later. If I'm not up here, I'm probably down in my office at 265. So, that then leads to, what are my hours? Well, this week is a regular class week, so same as all hours have been, with one exception. Friday, I have a doctor's appointment. I think my wife said it was 9:20. So that means I'll go to work on the Birmingham campus at 8 o'clock, and I'll stay there until about 8:40, and then I'll have to leave to go back to UAB, the Kirkland Clinic, or Whitaker Clinic, whatever one is Whitaker, right next to Kirkland, and I will have my doctor's appointment. I don't know how long it'll take. Sometimes they get behind, don't they, Patrick? Okay. And sometimes things take longer. I don't know if he's going to want blood work done and other lab work done. It's my annual physical, and he missed it. It was scheduled for last spring, and he had to cancel it. And so I say, well, what's the next available date? December? Well, no, I think it was actually October, November. I said I need it on a Friday. December, so that's why it's coming up now. So he may want more lab work or other stuff. I don't know. That may take longer. Or I may get out of there in record time, I'm hoping, and then I'll go back to the Birmingham campus and be there at least till noon. If I don't get through the doctor until afternoon, I'm not going back to campus, okay? Or I'd say even after 11:30, because by the time I drove from there to Birmingham campus, it'd be 12, and I'd have to leave again. So.
You don't have to get the graduation?
What's that?
You don't have to get the graduation?
Oh, okay. This is this coming Friday.
13th.
Graduation is the 13th. Yeah. What time is graduation? 1 o'clock. Okay. Yeah, I'll be here for that one. So I'm still on this Friday, not next Friday. Okay. Yeah. So that's this Friday. So that's the one exception to my office hours this week. I'm not going to be there 8 to 12 like I normally am. I'll be there 8 to 8:40. So that's when you catch me. And I'll come back to campus if there's time after my doctor's appointment. Okay. Now let's talk about next week, final exam week. On Monday, I am free all day long. I'll be in my office from 8 till 6, all day long. All my classes that day are doing take-home finals, and they're bringing them in to me. I'll be grading papers like crazy. Okay, Tuesday, I have a final from 8 to 10, approximately 8 to 9:50, down in 205. So if you're looking for me Tuesday morning, 8 to 9:50, I'll be at 205, administering the final. Okay? It may actually go a little later, so if I'm not back in my office at 10, check 205. Okay. Then I'll be back in the office whenever that's over until this class starts at 3:15, because we have regular class Tuesday, so I've already said, at 3:15. Well, I will be leaving a little before that to go get the pizzas and come back. So, but we'll be here at 3:15 until we finish everything we're going to do. Then you'll be leaving. Then I'll still be here until 8 o'clock, okay, like I normally am. Then on Wednesday, have absolutely no finals. People will be turning in finals all day. So that will be from 8 o'clock in the morning until 4 o'clock in the afternoon. At 4, I have to leave and go to the Birmingham West campus, and there is my final exam for the physics class, 4:30 to 6:30. So I'll be over on the Birmingham East campus, I may have said West, East campus, in the nursing or the health building, health profession building, in room 103. I'll be there from 4:30 to 6:30. 4 to 4:30, I'm traveling between campuses. Okay? Then, Thursday, I have absolutely nothing from 8 o'clock in the morning until this final at 3. So I'll be in my office 8 to 3, and then we'll be from up here administering the final until people finish, which probably won't be past 3:30 or 4. It's not going to take that long to do the final. And then I'll be here till 8 o'clock that night. So I'll be here, and then Friday I'll be on the here they are. Okay. Logan's here. Even Jay came in. And Frank's here. All right. Now, that gets me to Friday. Friday, I'm on the Birmingham campus from 8 to 12, and then we have the graduation at 1 o'clock. How long is it supposed to be? About an hour? Hour and a half?
I've heard about 2 hours.
2 hours? Okay.
I guess it would depend on the number of graduates.
Yeah. And how long the speaker is. And whether Ethan shows up, that kind of stuff. Now, okay. All right, any questions on how we're going? Oh, okay. That gets us through Friday. Grades are due in now for graduates, grades are due in earlier, so it won't be any problem getting yours in. Are you the only graduate? Oh, Ethan. Yeah, I won't have any problem getting yours in either. Anyone else? Okay. And I don't even think there's any special thing for y'all because you don't really get the diploma at that time anyway. It's mailed to you later or you come and pick it up because that's just a ceremony. You'll get a rolled up piece of paper and show, and that's it. You know, it'll look official, but that's all. Huh?
I said, thanks for telling us there's no Santa Claus.
You got it. Okay. But then grades are due in by noon on Monday. So anything I don't have by noon on Monday, in fact, by the end of the week on Friday, because I'm averaging grades and putting grades in and that kind of stuff on Monday. If you do turn in something then and I have time to grade it, it'll get done. But there's no guarantee. So try to have everything in by next week. And
that's this Friday?
No. Okay, that's the following Friday, finals week. And then after that, of course, we're here on Monday doing our grades and stuff. We're also here Tuesday and Wednesday. So if there is anything you need to see me about, or if you didn't have everything in and I give you an incomplete, you can come and bring it in, then I'll change the incomplete and it'll get changed in time before next term. So I will be here Monday, Tuesday, and Wednesday of that week after finals. Y'all aren't required to be here. No classes, no finals, anything, but faculty are required to be here. So we'll be here Monday, Tuesday, and Wednesday. But after that, not, okay? Won't be back until early January, the 3rd or something like that, I think. Okay. Now, for those who just came in, I'm not going to go through all that again, but here are the highlights. Pseudo-course evaluations are now open. Please do them. Please do them. All of them. Everything they ask you to do. Doesn't take that long. Has anyone already done them? You have. How long did it take?
Probably 5 minutes.
Okay. Second?
Just not very long.
Not very long at all. Okay. Now, please do the pseudo-course evaluations. Okay. Today in this class, we're going to finish chapter 6, start chapter 8. Okay. When we get far enough along in 8, or I run out of voice or something like that, we may end a little early. Sorry about that, folks. Okay? And then on Thursday, we'll finish chapter 8, and I think that's about all we'll have to do. Oh, and have the test on chapter 6, because we're finishing 6 today. So we'll try to get at least half of 8 done today, the other half done on Thursday, and then the test on chapter 6 on Thursday. All right. Tuesday of the following week, you'll come in, and we're going to have pizza, okay? So Thursday, let me know. Everybody be here. Let me know what kind of pizza you want, and we'll try to get that done, determined then. So Tuesday, we'll have pizza, and I'll be returning all the papers to you. So every test, every lab has to be complete and turned in before class on Tuesday of next week, 1 week from today. Okay? And then once all those are returned and you finish your pizza, then we'll do the lab for chapter 8, and then we'll do the test for chapter 8. Okay? Now, I'm making it optional. If any of you want to take the final exam Tuesday, it'll be ready. But it's not required. It's not even scheduled for then, but for people who do have to leave or various things like that, especially the graduates. That gives me more time to get them graded before you graduate. So, because if we wait till Thursday, that's just 1 day. So that will give us more time. And then, but technically the final exam is Thursday a week. Thursday of next week. I'll be here from 3 o'clock until everybody's through. Okay? And then I'll be in my office till 8 o'clock at night. Okay? Any questions? All right. Let's hit the chapter 6. All right. Now, where we left off, any questions on chapter 6 so far? It's a long chapter. We've done 3 labs in it. And the last thing we did was example 611 on page 167, and it continued, 167. We did talk a little bit about solar cells on 168, and we talked about why this slide is. Okay. We talked about resistances in circuits. And what kind of resistance setup is this? Let me go back. What kind of resistance setup is this? Say again? This is in series because the same current goes through each resistor. You add more resistors on the circuit, same voltage, more resistance, the current goes down every time you add another resistor. Okay? So the resistors add, the current drops as you add more of them, and the voltage stays the same. The same current goes through everything. We talked about that last time, and we did example 611, which dealt with that kind of circuit. Okay. So resistances add in series circuits. So what kind of circuit is this? Parallel. Now what happens now if you add more resistors to it? Anybody? What happens to the current? It increases because you got the same voltage across every one, and the same voltage, whatever your resistance is there, that's going to demand more current. Every time you add another resistor, that requires more current. Voltage stays the same, and voltage across each resistor is the same. Now, if you got the same voltage and more current, what it seems like is your resistance is going down. And indeed it is, because these resistors add this way, by reciprocals. Okay? This is your total resistance, or the effective resistance of the whole circuit. And 1 over that is equal to 1 over the first resistance, plus 1 over second, plus 1 over third, and it's on and on and on. And here's what comes out of it. You got more than one circuit path available, so you got more current to go through each path. Overall resistance drops as more elements are added. Seems strange, but it's true. The total circuit current increases as more elements are added. So this R total, I'll give you a hint here, is going to be less than any single resistor in the system when you're on parallel resistors. Series resistors, this is going to be greater because you're adding all those together. Here you're adding the reciprocals and then taking the reciprocal of your answer. So that's actually less. It's rather bizarre. So let's do the same thing that we did for the series resistors, example 612. That's what we left off last time. Assume that the 3 resistors in example 611 are now connected in parallel. Okay? So they're going to be connected, like this. Okay? Now, if I leave that up there, we don't have room to write. So this is what it's going to look like. So let me back up and do the writing here. What we had before was a 12 ohm resistor. Let me get my pen set up. All right. I'm going to try to do a smaller picture than we have here. So let's have a battery. I'll do it this way. The battery here, okay. 1 resistor here in parallel with 1 resistor here in parallel with 1 resistor there. Okay. R1, R2, R3. Okay. R1 was 12 ohms. R2 was 8 ohms. And R3 is 24 ohms. Okay. And I believe it was still a 12-volt battery. They don't say specifically, but they said same circuit, so we're going to put a 12-volt battery. So this may have more than one cell, but I'll just put 12. They sometimes call it E, they sometimes call it V. I'm going to call it V is equal to 12 volts. Okay. That's the setup. Now connect in parallel. What is the combined resistance? That's the first thing they're asking. Someone tell me what the formula for that is. Just had it up there a short while ago. And you can't read it. No, that's series. This is 1 over R1 plus 1 over R2 plus 1 over R3. Okay? So 1 over what they call R total, I like to call it RE, effective resistance, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And we just have 3, so there's no dot, dot, dot. Okay? Now I'm going to show you a couple ways to do this. This is 1 over 12 plus 1 over 8 plus 1 over 24. Gives you 1 over RE. And that's what we're looking for. Now, I can show you how to do it manually. It's doable, and it's not that bad. But it is a little messy. Okay? And then I'll show you how to do it on the calculator. Okay, first you tell me, what would be your approach here? What would be the first thing you do when you're adding fractional forms? Anybody? Common denominator. What's the common denominator between 12, 8, and 24? 24. So this will be 24 here, 24 here, and 24 here. Now, how many 24ths is 1/12? 2. Easy way to do that is 12 into 24 is 2. 2 times 1 is 2. Okay? And here, believe it or not, is Latricia. All right. Welcome back. Okay. So we're only missing Mendez and Diamond. How many 24ths is 1/8? 3 24ths. Okay? And and Diamond came in. Now we're just missing Mendez. And he actually came by earlier today. And now I was in here. I don't know where he is. Okay? All right. And how many 24ths is 1/24th? 1/24th. I was going to say the easy way to do this is 8 into 24 is 3 times 3 times 1 is 3. So that's how you get that numerator. Now, let me go on and do it again. I'll probably have to do it again when Mendez comes in. But let me hit the high points for you who just came in. Student course evaluations are now open. They finally opened them yesterday. Should have been open for weeks now, but they finally opened them yesterday. Please do the student course evaluation. And Logan has done his. He said it only took a number of minutes, so it doesn't take long. Please do student course evaluation. Okay? Number 2. We're going to finish chapter 6 today. That's what we're doing now. We're going to start chapter 8 today. Hopefully get at least halfway through chapter 8. And if and when we get that far, and if y'all are tired and I'm tired of talking and my throat's going out on me, we may just end it a little early today. Then Thursday, we will meet again. And on Thursday, and because we're finishing chapter 6 today, that means we have the test on chapter 6 on Thursday. But before we do that, we're going to finish chapter 8. That's why I want to get at least half of it done today so we can finish chapter 8 on Thursday. Okay? Then when we finish chapter 8, we'll have the test on chapter 6. And once you've done that, that'll be it for Thursday. Okay? So some of you may even get to head home before it gets too dark. Okay? I doubt it, but it gets dark so early. But anyway. Next. Tuesday of next week is our last day of class. Everybody else is doing finals, but we're on our last day of class. And what we got left to do, and this is the important part. Well, number 1, we're going to eat pizza. Okay? So I'll try to have that here at 3:15. Okay? And actually, since we've got all but one person here. What do any of you have any restrictions on what kind of pizza or preferences? What types of pizza would you like?
Cheese.
Say again, cheese? Okay.
Meatloaf.
Cheese only, you said? Okay.
Meatloaf.
Meat lovers? Okay. I think at Little Caesars they have 3 meat pizza. Okay. 3 meat pizza.
Supreme.
And what?
Supreme.
Supreme?
Mm-hmm.
Do they have that at Little Caesars? I think their Supreme is the meat lover. I mean 3 meat. I think. If they have something else, I'll get that one too. Anything else? What's that?
I said I'm with the third brother. I don't eat pork, so that's good. Cheese is good.
Cheese is good. Okay. Yeah, that's why I was asking. Okay. All right. So, how many do you think we'll need for this number of people? Maybe plus 1. How much? 4? I hear 4. So I heard more cheeses than anything else. So 2 cheeses, 1 3 meat, and if they have a Supreme. If not, I'll get a second 3 meat. Is that right? Huh? A pepperoni. Okay. Any other choices? So 2 cheeses, 1 pepperoni, and 1 3 meat. Does that do it? Okay. Is that all right? Okay. So that'll be next Tuesday, 1 week from today. And while y'all are eating your pizzas, I'm returning every lab and every test, which means I need to have every lab and every test done before class next Tuesday. So you got this week, you got Monday, and you got Tuesday morning and early afternoon to get your labs and tests completed and in. Okay, because once that class starts, I'm returning those to you. Okay? If you are still taking a test or doing a lab or something, you're not eating pizza. So, I mean, you can come back and get it. There usually will be plenty. Okay, now, then, once the papers have been distributed, the pizzas have been eaten, then we're going to have the lab for Chapter 8. Then we're going to have the test for Chapter 8. And that's all we have to do, returning papers, lab for Chapter 8, and test for Chapter 8. That will be it for Tuesday. Unless some of you want to take your final exam, if there's time left, which I think there will be, you can certainly do that. I'll have the final ready that day. Okay, but if you don't want to take it then, you don't have to. The final exam is scheduled for Thursday of next week. Not this week, but next week. Okay? And then, once everybody's done the finals, grades will be in by Monday noon. So if you didn't get everything in or missed the final or something like that, you need to get everything done by Monday, before Monday noon, because that's when grades go in. But I'll be on campus Monday, Tuesday, and Wednesday of that next week. Okay, all week next week, but Monday, Tuesday, and Wednesday of the following week. Okay, and graduation is not this Friday, but next Friday on in the gym, right, at the Birmingham West Campus. And one other thing, this coming Friday, I have a doctor's appointment at 9:20. So I'll be on the Birmingham campus until about 8:40. Then I have to leave to go back to Birmingham to the clinic. And then I'll have my doctor's appointment. If we get through in time, I'll go back to Birmingham West. If we don't finish in time, I won't go back at all. Okay, so you can catch me 8 to 8:40 Birmingham campus this Friday, and then hopefully I'll be back, I don't know when, maybe 11 to 12 or something like that. But if they take too long, then I won't. Okay, any questions then? All right, you're up to date. All right, so let's finish this problem. So when you add these 24ths together, this is example 612 on page 169, that adds up to 6 24ths, right? Well, what is 6 24ths? Reduce it, 1/4. So 1 over RE, effective resistance, the book calls it E total, whatever you want to call it, is equal 1 over 4. So therefore RE or RT, however you want to call it, is equal to 4. 4 ohms. Isn't that amazing? You have 3 resistors, 12, 8, and 24, and the effective resistance is 4 because these are in parallel. If these are in series, you add them up. That would have been 44, okay? If these were in series. In parallel, effective resistance is 4 ohms. Okay, so there's the answer to the first part of that problem. What is the combined resistance? 4 ohms. As opposed to in series, 44 ohms. So that's the A part. The B part. What is the current in the overall circuit? How do we determine that? Anybody? What is the current in the overall circuit? Say again? What would we use? Good old Ohm's law. How does Ohm's law go? If you're looking for current, that's I is equal to V divided by R. And what's your voltage? 12 volts. What's the resistance? 4 ohms. And what's your current? 3 amps. Whoa! What was it last time when you had these same 3 resistors in series? It was, I know it's on here somewhere. Oh, there it is. 0.27. Just slight bit more than a quarter of an amp. And now we got 3 amps. Okay? C. That's yes in Spanish. Okay? What is the current through each resistance? How would you figure that? Let's do I1. That's the current through resistor 1. What would that be? It'd be V over R1. And V is still 12 volts divided by what's R1? 12 ohms. Okay, so what would be the current? 1 amp. Okay, I2 would be V over R2. Now you see why it's V. The same voltage across this one is across this one is across this one. That is, the voltage is the same all the way across. Okay? So what is your V? Same as it was. 12 volts divided by what's R2? 8 ohms. 12 divided by 8 is? That would be 3 divided by 2. 1.5 amps. And finally, I3, can you read that? Is equal to V over R3. And what's V? Still 12 volts. What's R3? Help me somebody. 24 ohms. And 12 divided by 24 is? Half, 0.5 amps. Hey, let's add up our 3 currents. 1 and 1.5, that's 2.5, and another half is 3. There's your 3. There's where the currents go. 1 amp through this one, 1.5 amps through this one, half an amp through there. There's your 3 amps in the whole circuit. A nice way to check it. Okay. Any questions? And that's exactly what they got in the text, too. All right. Now, any questions? All right. Moving on to the last section in the chapter, household circuits. okay? Generally, in your household, or rooms, or wherever, your circuitry is kind of a mix of parallel and series. Mostly things in parallel. However, some things have to be in series. So it's a combination of some things in series and some things in parallel. In this room, what would be in series? Any guesses? The light switch has to be in series with the lights. Otherwise, if it's parallel, you flip the switch and they do whatever they want to. But that has to be, so you flip the switch, it cuts the entire circuit. Okay? Well, we have two switches. This is for this bank is off, that bank is on. How about the lamps themselves? Parallel or in series? Parallel. You pull the bulbs out of one, the others stay lit. If they were series, you pull the bulbs out of one, they all go off. Remember, you did that in lab. Okay? So the light fixtures are in parallel, but they're all in series with the switch. Same thing about the plugs in here. They're probably all on one circuit, or at least those two are, but they're in parallel because you unplug one, the others keep running. Okay? So those are usually parallel. Now they added this one later. I don't know if they put it on the same circuit or a different circuit, but don't know the answer to that. Okay, so the light fixtures in the room are in parallel, usually. If you're a Christmas tree in the old time, they would be in series, but we don't do that anymore. The appliances are typically in parallel. Otherwise, you turn one off, they all go off. We don't want that to happen. The same voltage is applied available to each one because they're all set up to run on that same voltage. Okay? Now, in the old days, they had fuse boxes. Nowadays, they have circuit breakers. Okay? Mostly. Okay? The circuit breakers and the fuses prevent overloads. Because if you kept adding circuits to the same receptacles or loads to the same circuit, after a while, remember, if they're all in parallel, and you keep adding more, it's demanding more and more and more current. After a while, you've got more current than the wires can handle. They may get very, very hot and catch something on fire. The circuit breakers are there to prevent that from happening. I had to buy a circuit breaker over the break, and just by all the ones in our box, the box I was having to mess with were 20 amps. Okay? Down in the house, some of them 15, some 20. A few of them may be more, especially for big appliances. Now, let me tell you a story of the first house my wife and I lived in when we moved to Birmingham. We were renting it. It was a grand-looking old house. Operative word there, old. Okay? It wasn't a very tight house. It was old. There were some areas you could look through. They had an old, I guess, floor furnace or something because there was a grid. And you could look at certain angles and look through the wall of the crawl space and you could see light through it, not the tightest of old houses, okay? But as I said, it was old. And we typically had one and maybe two receptacles in each room. Sort of like this. Originally, there were just two receptacles, one over there, one over here. When they put in this stuff, they put in one more over here, okay? But a lot of rooms only had one receptacle. So we had drop cords going everywhere, extension cords in every room so we could plug various things in. And that worked okay. A little scary, but okay. But they said we upgraded the kitchen. So they had many more receptacles in the kitchen. I mean, they had lots of receptacles in the kitchen. Of course, they needed one for the fridge. I can't remember if the stove was gas or electric. It's been a long time. At least part of it was electric. And then they had plugs that you could have microwaves and coffee makers and can openers and whatever you needed. There were plugs scattered all over the kitchen. Okay. But what we found out, they had taken the same old circuit that had been in there when there was probably only one plug, and they just put more and more and more plugs on it. And they had a fuse box. They didn't have circuit breakers. And what we found out, if the microwave was running when the compressor on the refrigerator kicked in, it would be going when the compressor turned off. And if the toaster oven was on when the microwave was on, everything went off. Or when the refrigerator kicked in, because the circuit couldn't hold it. I kept, the drugstore at the time was Big B. Did any of you remember Big B? Okay, I kept Big B in business just buying fuses, because you never knew when something was going to kick on. We knew better than to put too many things at the same, but when we had something running, like maybe the coffee maker, and then the refrigerator compressor kicked in, there it kicked off. Because it wasn't, they just put more plugs on the circuit that was a very weak circuit to begin with. Okay? You don't want to do that. Now, somebody said, I just put a penny in the, no! Then it will overheat. You'll get too much current through there, and we didn't want fire on our hands. So we just kept a supply of fuses and tried to minimize not running anything more than one thing at a time, but we never knew when the refrigerator compressor was going to kick in. And if it did at the wrong time, there went another fuse. Okay. But the switches have to be in series with whatever they're switching, like the light. Okay? So you do have combinations of series and parallel. Okay. And that, of course, is AC, so you usually will have a ground. We haven't talked much about AC, but there's where that is. Any questions? Okay. Now, household circuit safety. Many things have changed over the years. The old house we're in now, I had to buy a couple of, Thanksgiving week was repair week, okay? Catching up on deferred maintenance. Most of our plugs in our old house we're living in now that we bought, not renting, most of the circuits are two-prong circuits. They didn't have the third prong. And most of them had the same size holes, for the plug to go in. And this is illustrating a couple of differences. Okay, what you have in a household circuit is a potential difference from two different wires per device. This is the hot wire, this is the ground. Now, for the life of me, I would have thought the hot wire would be the big one and the small one would be the ground, but no, it's the reverse of that. And these circuits here are wired such that the hot side is here and the ground is there. In the old days, they didn't seem to make any difference. They put same plug on both, same size hole on both. You just plugged it in, and it was alternating current anyway, so they didn't really care. Nowadays, they pay more attention. So one of these is an energized load carrier, that's what I call the hot side, and the other is the grounded or the neutral wire. Okay, that's what this plug is. The energized load carrier and the neutral ground. Okay, but this plug actually has a third prong. The third prong provides another grounding wire, which is an added safety element. Okay, this one, if you overload the circuit, it's all going to ground, But if you have the third one, that's an additional ground that will bleed off some of the excess. Okay? But there are even other things. Okay. Number one, the polarized plugs that you put the hot in the hot and the ground in the ground. That is an improvement over the old days in our old house when they're all the same. In fact, sadly, because all the old plugs that are in the house that we haven't replaced, they're the same, and when you have a piece like this, you can't plug that in because it's the same size as that one. So you have to have an adapter, which really is a cheater, that has these two the same. But So you're defeating your own purpose there. Okay. But, so that's one other device, polarized plugs. The other is a ground fault interrupter. Anyone know what that is? Okay. That's a device, and if this worked, you'd have these two plugs separated with sort of a bar in between. And that bar usually has at least two buttons, maybe three. Okay? One is a test button and one's a reset. I don't know what the third one is. I don't know. But anyway, if you put too much current in that one, the whole plug will shut off. Okay? And that's called a ground fault interrupt. This has potential for saving you from some shocks, but the ground fault interrupt basically is supposed to save you from any shock. When I was growing up, there were mystery shows on television a lot. And one of the classic ways that someone, say, a woman was tired of her husband or he was abusive or something like that, and she wanted to bump him off while he was taking a bath. They didn't do showers much back then, taking a bath.
Throw the radio in the tub.
Second?
Throw the radio in the tub.
Throw the radio in the tub, throw this shaver in the tub, something that is electrical in the tub, electrocuted. Oh, he must have knocked it in there. It was an accident, you know. I just heard the noise and went up and he was dead, you know. That was a classic way of bumping someone off. Supposedly, a ground fault interrupter will not let that happen, because as soon as that surge happens, it shuts down the whole circuit. In the old days, they didn't have that. That's why, where do you find these ground fault interrupts? Say again?
Bathroom and kitchen.
Bathrooms and kitchens, where there's lots of water, and one other place, your outside circuits quite often have ground fault interrupts. Anywhere that there's a large potential of water being in connection with the circuit. So that's what the ground fault interrupts are. Now, I have a younger brother who worked with electric companies, retired now. He hated ground fault interrupts. I never knew why. He said he disabled everyone in his house. Duh, I don't know why, but that was his business, and he hated the thing. Maybe the early ones weren't very reliable, or they gave him lots of problems, but I don't know. I know in the house we have over in Georgia, it's a fairly new house, so all the outside plugs have our own ground fault interrupts, but only one's the master. So when the circuit goes out, you have to find all the outside ones to find out which. Now we know which one it is, but the first time they went out, we were looking for every one. We didn't know one of them had one. That was the one that was the master. So they can be a pain in the neck sometimes. But I wish they'd have wired them so each one cut itself off and that's alone. Okay. That's the end of the chapter. Any questions on chapter 6? Now, I say it every chapter. Nothing replaces reading the chapter. So if you haven't read it yet, shame, but read it. Okay? And once you've read it, then there is a summary, and this is a fairly long summary. It was a fairly long chapter. Almost a full page in itself, though a little bit short of that. They have a summary of equations, more than most, 11 equations here. And some of those equations can be written multiple different ways, so it actually comes out being more than 11. Key terms, this list is about average, I guess. They list them alphabetically, but they do have the pages on which they're first introduced or defined. But then applying the concepts, this, in my mind, is going to be your best source of a study for this chapter. It's 50 multiple choice questions. Most of your questions on your test, not all of them, most of them, the chapter 6 test, which we'll have on Thursday, will be multiple choice. I doubt if any of them are exactly these, but they'll be asking from the same. If you know these, you're probably going to know those as well. They'll just be asked a little differently. Okay? So anyway, those are the best thing to study for your test. They provide the answers at the end. Don't look at the answers. Try to figure out the answers first, then go through and check your answers by the back. If you can't figure out why those are the answers, be sure to ask in class before the test on Thursday. Questions for thought? There's actually fewer than normal, only 12 there. For further analysis, maybe 1 or 2 more than normal, 7 of those. Then there's an invitation to inquiry, earth power, certainly something if you'd like to read that you can. The parallel exercises are a lot like the examples we've done in the text. Unfortunately, if you have a little book, I asked them to put the answers in the back. I don't think they did, but those questions are a lot like the exercise examples that we had during the chapter. Those are good to do too. There will be at least 2, maybe 3 actual very simple problems to do. So bring your calculator. You can probably do it without a calculator, but it makes it a little easier if you had a calculator. Now, I wish we had time for chapter 7, light. It's a very interesting chapter, but obviously we don't have time for it. So we're going to skip chapter 7. In fact, your little books don't even have it in there. However, you're welcome, if you got a bigger book, to look through it. One person who's listed there is James Clerk Maxwell. Looks like it's Clerk, but it's pronounced, he's Scottish. They pronounce things strangely. It says a British physicist, but he was born in Edinburgh, Scotland. In fact, that looks like Edinburgh, doesn't it? Speak with any Scottish person, it's Edinburgh. There's no extra syllable there, but they pronounce it if there is. Scots, 2 things are on the way. Okay. All right. So we're skipping chapter 7, moving on to chapter 8. So let's us do the same. Any questions on 6 before we do that? All right, so let's go to chapter 8. Last chapter we'll do. All right. We'll go from current slide. And this picture is not quite the same one that you see in the book. Your book is from an older edition. But it's chapter 8 is atoms and the periodic properties. The core concept, which is on my page 205, whatever it is in yours, is different fields of study contributed to the development of the model of the atom. Now that's a real nebulous kind of core concept, but you'll see we are talking about physics, chemistry, all sorts of things, bringing things together. And it's not just the model of the atom, but how nature is modeled. And we'll talk about that as well. Okay? Now, 8.1, first section here, atomic structure discovered, hypothesized, talked about, whatever. The ancient Greeks. Now this goes back to Democritus, who came along before Aristotle, who we talked about so much. Okay, Democritus, 460 to 362 BC. Boy, if my adding's right, that's 98 years old. Whoa, okay, pretty old dude. He first hypothesized, and I've taught this in several chapters so far, that particles, that a material can be broken down and broken down and broken down and broken down and broken down, broken down more and more and more and more and more. But at some point, you get to, and this is all fault for him, at some point you get to the smallest particle possible to still be that material. Iron, copper, nickel, whatever. Okay? That was Democritus's idea, and he called that smallest particle that can't be divided anymore, indivisible, an atom. And that comes from the Greek word that means indivisible. Okay? That's where we get the name atom. Nothing modern, 400 BC. Okay? Way back. Okay? Now, about a couple generations later, along came Plato and Aristotle. And they took over and said, nah, there's no smallest particle. Matter is continuously and infinitely divisible. Okay? Where they got that and what the basis was, I don't know. But they basically poo-pooed what Democritus had said several generations before and said, no, matter is continuously and infinitely divisible. You can just keep dividing as long as you can divide, okay, and it still matters. Well, I'm going to add this one, and we've talked about it before. Aristotle came up with the notion, and Aristotle was, everybody believed, remember, that there were four basic elements in nature: earth, wind, fire, and water. Okay? And three of those made a scene, right? Okay. Now, back in my time. Well, as scientists got maybe a little more time on their hand and started studying that and looking at it and increased their abilities. Now, this is still BC back then. Something like 2,000 years later, scientists were beginning to experiment and do other things and said, look, if those are the four basic materials, they're all pretty cheap. Earth, you can go out and dig up. Okay? Water, you can go out and dig up. Wind is everywhere. Absolutely free. Fire, it takes a little expense to heat things up, but you can do it. Pretty cheap. Burn wood, burn coal, and you can get fire. Okay? If that's all there is, folks, then we should be able to manipulate these four cheap to free elements to get anything we want. Gold, silver, platinum, mercury, zinc, whatever we want. So they started the process of manipulating. They ground them up, they burned them, they heated them, they mixed water with them, they diluted them, they did this, they did that, they did everything they could. And as they did, they found out, hey, we need to keep really careful notes so we won't reproduce what we've just done. But we need to get rich quick. These were entrepreneurs of their days, So they were keeping careful records. And over time, many contributed, but John Dalton came up to, and many others came up to the same thing. Hey, folks, there's way more than four elements out there. We can't manipulate these things to get them to do what we want to, but we do notice certain features. One of these features is, it's called the law of definite proportions. If you had carbon and oxygen, okay, and you burn the carbon in the presence of oxygen, you would use up just so much oxygen to burn so much carbon. If you had excess oxygen, all the carbon would burn and you'd have oxygen left over. If you had excess carbon, you'd use up all the oxygen and you'd have carbon left over. They always combine in some law of definite proportions. Well, John Dalton took that and he reintroduced the atomic theory to explain those chemical reactions that always had definite proportions. Now, here was his model. I've told you this before. He probably knew it wasn't completely accurate, but it fit the need for what he was doing. He said every atom has so many hooks on it. He's looking at all the different reactions. He said carbon has 4 hooks. Oxygen has 2 hooks. Hydrogen has 1 hook. Every atom, he came up with how many hooks because he studied how they combine together, and they combined by hooking up with each other. Okay? And that was his early idea of atomic theory. Okay? Now, along about now, they had determined, I think there were something like 37 elements they could define. Lavoisier, a Frenchman, put together the first sort of comprehensive list, and he missed on a few of them. And of course, there are a lot he didn't even know about, but that's what he did. Now, let's see if they lose this. Yeah. Why is this picture here? This is not an accurate picture. It's a representative picture. This represents the nucleus. What's wrong with this picture? It's way too big. The nucleus, if this was the cloud of electrons around it, I don't know if you can see from where you are, the nucleus would be an incredibly tiny speck in the middle. Okay? And that nucleus is made up of protons and neutrons. I don't know which is which. The dark ones are one and the light ones are the other. I'm going to guess the light ones are the neutrons and the dark ones are the protons. It doesn't matter. Okay? But these are incredibly tiny. They're incredibly massive. They have all the mass of that atom is located in that nucleus. Okay? But all the volume is occupied by this cloud of electrons. Now, this shows lots of little specks, but guess what? There's probably only 4 electrons out there because you have four protons. Okay? And the number of protons always equals the number of electrons for a neutral atom. We'll talk about ions later. For neutral atoms. So the scale of this is completely off. This is just representing a nucleus and a cloud of electrons. The reason they have so many specks, you never know where the electrons are. You know generally where they're located, but they could be anywhere in there. It's a probability argument, which I don't care for. Okay. The nucleus, though, is pretty much fixed. Okay. Now, so that's the model. Don't let that fool you. Okay. And actually, if you could see what I see, okay, figure 8.1, this is the one in the book. You see there is one cloud here and then another cloud out here. I don't know if you can see it from where you're sitting, but in the book you can see that. Now, that's close to true, except these little specks aren't electrons. They're places the electrons could be. There are only 2 electrons in this inner cloud and 2 electrons in the outer cloud. Now, if this is 2 and 2, then if I'm guessing right, 4 protons, 4 neutrons, and 4 electrons. That would be beryllium. Okay? Now, no guarantee this is beryllium, but that's what it looks like to me. I can see 4 light blue, I can see 4 dark purple or whatever, and you can't tell here, but that would be 2 inner electrons and 2 outer electrons. Okay? That would be beryllium. It doesn't have to be, but whatever it is. Okay? That's way beyond where we are now. Whoa. So here were the features of Dalton's atomic theory. Going back to Democritus, all matter is made up of indivisible electrons. Indivisible atoms. Okay. Now, an element, these things you see in the periodic table, every element has identical atoms. There are no stray atoms in there. Now, of course, there are always a few strays, but they would be contaminants. But an element is made up from identical atoms. All of them are just alike. Okay? Different elements have different atoms, have atoms with different masses. Now, that's originally what they went by, was mass. Okay? And in your periodic table, and that's the place to go to look for this, in your periodic table, sure enough, now this is on the back cover of my book. It's somewhere near the end of your book as well. But the masses are the numbers at the bottom here. Hydrogen is a 1, there's a decimal on it, but don't worry about that. Helium 4, lithium 7 is 6.9, so I'm around that at 7. Beryllium 9, boron, and on and on and on. Okay? These are the masses. And sure enough, they're right. All the atoms have, of different elements, have atoms with different masses. Okay? Now those are elements. Chemical compounds, compound meaning, com means with, pound is pounded together, no, that's not what it means. Okay, compounds are made of atoms in specific integer ratios. That's that law of definite proportions there. Specific integer ratios. For instance, carbon dioxide, 1 carbon, 2 oxygens. Carbon dioxide. Water, H2O, 2 hydrogens, 1 oxygen. Ammonia, 1 nitrogen, 3 hydrogens. Okay? Every compound is made up of atoms with specific energy ratios. That had to do with Dalton's hooks. They could hook together in certain ways. Atoms are neither created nor destroyed in chemical reactions. Atoms are not created nor destroyed. They're just shifted around in chemical reactions. Okay, for instance, if you had that carbon and oxygen, when you burn those, you're adding energy to it. Actually, it's releasing energy once you get it going. You heat it up and get it started, and then it starts releasing energy. That's because every carbon is connecting to two oxygens and making carbon dioxide. And you keep doing that until you get out of either the carbon or the oxygen. Okay? But the atoms are not created or destroyed, but they're changed. That carbon was black, the oxygen was invisible, the carbon dioxide becomes invisible. You think you destroyed the carbon. No, you didn't. You just changed its form. Okay? Atoms are not created nor destroyed in chemical reactions. Okay. Moving then to discovery of the electron, which is the first subtopic in 8.1. Along came a guy named J.J. Thomson. I don't know what J.J. stood for. Late 1800s. Okay, let's go back one slide, two slides. John Dalton, early 1800s. That would be about the time we were a fledgling nation at that time. He was over in England. Okay? J.J. Thomson, I believe, also in England in the later 1800s. Okay? What's happened there? We've had the Civil War and all that kind of stuff. So we're moving along. J.J. Thomson, he performed, now they have more sophisticated equipment, studying things. He performed these cathode ray experiments and discovered that there were little negatively charged particles that came out of atoms. Now, we said atoms are indivisible. They're indivisible to maintain what they were. As soon as you start pulling electrons or other things out, they're not that anymore. Okay? So these electrons, he discovered these negatively charged electrons. They had a charge. You could tell that, a negative charge. He could hardly determine any mass whatsoever. He knew they had to have some mass, but it was incredibly small. But he did measure the electrons' charge to mass ratio. A lot of charge to a very little amount of mass. He could determine the ratio, but he couldn't tell how much charge there was or how much mass, but he could determine the ratio. See what ratios are important? Our first lab. Okay. He identified the electron as that fundamental particle that carried that negative charge. That's the first part of an atom that he was discovered. Why did he discover it? Well, if you think back to our picture there, okay, let's go back to our picture. Right here. These electrons are flying around out here. These two are probably never going to move in here. They're so close to the nucleus. These out here are further away and shielded, so maybe that you could lose one or gain one. And if you did, you've got an ion on your hand. It's still beryllium or whatever it is, but it's no longer neutral because it either gained or lost an electron, so it now has a charge. But that's why the electrons are the things you discover first. They can be broken off, okay? And that's what J.J. Thomson discovered, okay? Here was his cathode ray tube. Now, a couple things that had to happen here. You put up a really high voltage between this end, the positive end, and this end, the negative end. Very high voltage. Very high voltage, okay? You also had to first pump out as much air as you could. Now, you couldn't create a vacuum. A vacuum would have collapsed the entire tube, but you pumped out as many as you could. And what he found was these charged particles left the cathode and went to the anode, flying down there. And that's why it's called a cathode ray tube, because these rays went racing down there. He couldn't measure the mass, he couldn't measure the charge, but he could measure the charge to mass ratio. Okay? And that's what he did. Very careful experiments. Okay? That was J.J. Thomson in his contribution. He discovered the electron. Okay? Now, here's basically kind of how he did it. Here's your cathode, and here's your anode. And the anode is actually a tube here, and it gets the electrons flying at a high rate of speed because it's a great, huge potential difference here between there. They fly down through the thing, but because there's nothing to bang against, they keep going. Here we have two charged plates, okay? One is charged positive and one charged negative. Well, he noticed that these things that are flying down here and make it through the tube, but they've got so much extra momentum they keep going. When they go through the charged plates, they're bent so that the negative charge moves toward the positive plate away from the negative plate. So therefore, he knew they had a charge. Okay? He also put this inside a large, strong magnet, North Pole, South Pole. Well, that also deflects the moving charge, because guess what? A moving charge is a current. Okay? And a current is affected by a magnetic field. Remember our last lab. Okay? So he reads on the screen over here, a detecting screen, and sees how much deflection you have, how much it's deflected up or down, deflected right or left, and between all these very careful experiments, he can determine the charge to mass ratio. Can't do any better than that, but that's what he did. The deflection depends on that charge to mass ratio, how much is deflected, okay? And he found pockets at different things, and that all depends on that charge to mass ratio. The positive and negative charges deflected in opposite directions because of the plates here, and also because of the magnet here. Okay? And that provided his experiment. A really clever experiment, especially since he basically didn't know what he was doing. He was just discovering things, okay? He knew there was something there. Okay. So that was late 1800s, discovery of the electron. Now, he only could get a charge to mass ratio. So here comes another guy, Robert Millikan. I think he was also British. This is early 1900s, around 1906. And here's what he did, a very clever experiment. Any of you ladies use an atomizer for, say, cologne perfume or something like that? Or how about when you're watering plants? Not watering plants, misting plants. Okay, you know what I'm talking about? Squeeze a button and the mist comes out. So he did this with oil. Okay? He called that an atomizer. Very, very tiny little droplets of oil. Okay? He sprayed these over, and they dropped through a hole in an electric field. Well, electric field is a flow of electrons. So some of the electrons attach themselves to the little droplets. Okay? And when they do, the droplets become charged. Okay? Now, if you had plates in there and had a negative charge on the bottom plate, positive charge on the upper plate, the droplets themselves aren't being affected by that. But once they get charged, then the droplets tend to go away from the negative plate towards the positive plate. And the charge on the droplet was always a multiple of whatever the electron charge was. Okay? So, he had the amount of charge that he had, plus J.J. Thomson's charge to mass ratio, he could then determine the electron mass. And that's what he did. It's a really clever experiment. So here's this little atomizer. Oil's in here. Sprays it out here. A few of the drops actually fall through the hole in the middle. The rest of them play out. It doesn't matter. As they fall down, here's the negative plate. There's a positive plate. And there's an electric field in here, meaning there's electrons going from the negative plate up here. They attach themselves to the oil droplets, and now the oil droplet quits moving because now it's negatively charged. It doesn't want to go down here. It gets positive down. So some of them stop, some of them go more slowly, some of them start rising, depending on the charge. And they always are multiples of that electron charge, so he can back it up and see what what the smallest of those charges were, and that would be his single electron, or that's what he assumed it would be. Very clever experiment. The first term that I went back to college after I got out of the Navy, I was starting my master's. I just was finding whatever courses I could. I needed a full load to get my GI Bill. Needed 20 hours, and I wound up just having to take a lab course, a physics lab course. And in that, we did 4 labs in the 10 weeks, and one of the labs was this, the Millikan's oil drop experiment. And it was pretty amazing to watch the droplet fall, suddenly stop, and then start moving up or hang where they were. And you had some pretty, not too heavy of math, but some math to do to figure what charge was on that, because you can measure the electric field. So that's Millikan's oil drop experiment. So from that, Thompson's result gave a charge to mass ratio, and like I said, enormous amount of charge and a very small amount of mass. So this came out an enormously large number, 1.7584. Wow. Back in that day, you have that much precision, that's amazing. Times 10 to the 11th. That would be 175,840,000,000. That's a huge number. Coulombs per kilogram. And this is kilograms, okay, so that is really a small number. Millikan's result, he came up with what the charge on the electrons were by the amount that it took to get them to quit dropping and start moving up. He found out what the charge was, recognized that number. We had it earlier, 1.60 times 10 to the minus 19 coulombs, okay? Back when we did Coulomb's law. That was the charge on the electron. That's an incredibly small number, okay? That's point 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 the decimal point. That's an incredibly small number. So when you combine these together, here's the charge to mass ratio, there's the charge, divide that by charge to mass ratio, the charges cancel out, and 1 over 1 over mass gives you this, and that's 9.11 times 10 to talk about a tiny number, 10 to the negative 31 kilograms. That's 0.00000000000. 30 zeros in front of that 9 before you get to the decimal place. That is a tiny number. That's how much mass is an electron. But no one's ever seen an electron, identified an electron, but we have figured out what its mass is and what its charge is. Pretty incredible results. Okay? Now, so here we have features of some of these components of the electrons. And the case study at the top of page 208 actually starts off with an English physicist named William Crookes, okay? And he used the Crookes tube. Later you'll see the name Michael Faraday. May run into him before it's over with. So there's several names in here, but then we have J.J. Thomson, and why they have this, the oil drop experiment was Millikan. He should be the one listed. Oh, there it is. He's in the middle part of that on page 209. Well worth a read. Pretty interesting stuff. Okay? So, early models of the atom. Okay? Dalton had said atoms are indivisible. This is early 1800s. Thomson and Millikan came along and found out that the electron came out of these atoms. You couldn't divide them and keep the same material, but you could pull out pieces of them. And this was a mass which is incredibly small. You couldn't even measure a volume. You couldn't identify one of these. They're just too incredibly small. So, what was the nature of the atom's positive charge? Because before you lost the electron, it was neutral. When you lost the electron, it became positively charged. What's the nature of that? Well, Thomson, J.J. Thomson, his model, and again, they came up with models because they could see atoms. No one could see an atom. Even with electron microscopes, you can't really see an atom. You can see a hole where an atom was, sort of, but you can't see an individual atom that I know of. So Thomson's model was the plum pudding model. That's very pretty sounding, isn't it? Okay, plum pudding model. That the electrons are embedded in a blob of positively charged matter like raisins in a plum pudding. So you had, I think of raisin bread. Okay, raisin nut bread, raisin bread, you know, where the dough is all around, the raisins are in there. The raisins are electrons that you can separate, but the rest of it is the positive. Don't take this to heart, it was wrong. But this was his early model. Okay? If that was the model, though, if that was what it was like, then along came Ernest Rutherford. Now, I'm pretty sure he was from New Zealand, or I believe it was. Ernest Rutherford. He said, if indeed that's the case, that you got this positively charged dough, and in the individual, very tiny little raisins, electrons, then what we should be able to do, and by this time they had discovered alpha particles. Now, you know what alpha particles are? They're the nucleus of a helium atom. Helium has 2 protons, 2 neutrons, that's in the nucleus, and 2 electrons. If somehow you can strip off those 2 electrons, then you have these alpha particles, particles that have 2 positive charges. Okay? So if you, and they did, they learned how to do that. So what we're going to do is fire these alpha particles that are charged, positive charge. So set up a strong electric field here, and the charges are going to go toward the negative. Now, the negative over here, the alpha particle source here, and fire them down the thing here. Now, we're going to put in between very thin gold foil. You know what aluminum foil is, right? It can be really thin. Gold foil, you can actually hammer out even thinner than aluminum foil. I don't know if you've seen picture frames that look like they're gold. And you think, wow, that's really good gold paint. No, what it may be is what they call gold leaf. It's just little, tiny flakes of gold you just smear on there, and you're actually seeing gold, but it's very little amount of gold, but it gives a very good color. Okay, anyway, very thin gold foil. So he said, if that thin gold foil is your dough with the electrons scattered among the dough, then you should get a pretty good deflection pattern of these alpha particles, you know, through that, because they'll be attracted to the raisins, the electrons in that thing, and you should get a decent diffraction pattern, and we can learn something about what kind of plum pudding gold is made of. Okay. So that was his plan. So, but what happened was he fired these positive charges through the gold foil, and guess what? Most of them went right through. Not being deflected, not bouncing off of anything, just went right straight through. He said, wait a minute, okay? These alpha particles are incredibly small, and gold is a heavy atom. They should be messing with it. And they didn't. Most passed through without significant deflection, but a few of them were scattered at huge angles. Whoa, how can you account for this? The conclusion is the atom's positive charges, that would be what was deflecting the positive alpha particles, they must reside in incredibly small, tiny little nuclei, but very massive nuclei. You know that electrons don't have any mass, or very, very little, hardly any volume at all. By the fact that most of these went through with no deflection, but a few, very few, were deflected way back. That means they did hit a nucleus and bounce back. That means that they're incredibly small, but incredibly massive. That's where we get that. Later, they found out the positive charges were protons. The positive proton, PP. Okay. Now, much later, that was 1907, shortly after Millikan, 1906. 2 decades later, 2.5 decades later, James Chadwick also found, I think he was British too, neutral neutrons, not negative neutrons, negative electrons, neutral neutrons. First 3 letters of the same, not 4 letters, 5 letters of the same. Neutral neutrons in the nucleus, along with those protons. That's what made them so massive, but very only positive, because these had no charges at all. Later, they found out the neutrons were actually slightly more massive, not much, slightly more massive than the protons were. Okay. Now, here's the incredible thing. All those electrons, whether they came from iron, hydrogen, beryllium, uranium, wherever they came from, the electrons are all the same. And, the atoms are very different. They're unique for every element, but these components, the protons are the same protons in all of them. The neutrons are the same neutrons in all of them. It's just how they're put together. And if you happen to have 4 protons, that's going to be beryllium. 3 protons is going to be lithium. 2 protons is going to be helium. 1 proton is going to be hydrogen. 8 protons, everything depended on the number of protons. We haven't gotten there yet, but I'll just put that out there. Those, how many positives, and they can be so very different. Okay. So here is Rutherford's gold foil experiment. So here's the source of, and actually alpha particles are radioactive particles. They're very weak radioactive particles. If you have a piece of paper, they're fired at your arm, a piece of paper is going to block every one of them, or most of them anyway. Gamma radiation don't go right through that, go through lead, but no. These are very weak. Those are alpha particles. The nucleus of a helium atom. Okay, they're fired here. Most of them came straight through. Just very few of them were scattered way back. And by studying the scatter pattern, he found out basically that the protons, the nuclei, are incredibly tiny, but incredibly massive because it really bounced them back really bad. And so this was basically his experiment. Okay. Now, here's a picture of the gold foil. Okay? Now, remember I said the dimensions on that first atom were way off. Okay? Because the nuclei, this is still way off. The nuclei would be even smaller than that, maybe a few pixels in the middle. I mean, just incredibly, incredibly tiny. And the electrons are just in a cloud around that nucleus. That takes up most of the volume, even though electrons have no volume of their own. They take up the volume of that. So most of those alpha particles just go flying right through without being disturbed at all. However, a few of them will hit the nucleus and be deflected, sometimes really strongly, sometimes off to the side like billiard balls, but most of them go straight through. Okay? Now, the gold foil is maybe, they've shown here, 3 atoms thick, maybe it was 5 or 7 atoms thick, but still, they went right through because there's so little space occupied by those nuclei. Okay. Now, I think I may have said this before. I'm teaching another physics class, so maybe I'll send it to them rather than this one. When my older brother came home from college, he was 2 years older than me. He had his first physics class his sophomore year. He had a really good professor. He came home and was really excited because the physics guy said this: most of everything is nothing. Okay? And that sounds so bizarre. But what he was saying, the entire mass almost of this atom is located in a tiny, tiny, tiny little nucleus. The electrons are flying around here with almost no mass at all. They have a little, but not much. And they're taking up an enormous volume. So that little mass in that enormous volume, most of everything is nothing. It's outer space, okay? It's just completely void of anything, okay? Most of the mass is right there, and most of the volume is here with nothing in between. Just a few scattered electrons in a huge volume. So most of everything is nothing, okay? Outer space. Even the densest atoms like gold, most of it was nothing. So, moving along here, let's talk about what the new model of the atom is. The atom with a very small but very massive nucleus, so it's the nuclear atom. The atomic number is the number of protons in the nucleus, and that defines what element you're talking about. Give me a number, any number between 1 and 100. 17. If it has 17 protons, it's guaranteed to be chlorine. You win chlorine. That's the only atom that has 17 protons. If it has 17 protons, it's chlorine. If it doesn't, it's not chlorine. Okay. Number of proteins determines the specific element. So, and those are in the nucleus. The elements are distinguished by this atomic number. Any other number? Some different element. Can't help it. They say here 113 elements are identified. I think in your periodic table in your book, the number, because this is a little more recent, goes up to 118. However, some of those that are UUO and UUS and UUP, those are unknown, so maybe they aren't identified. So count the number of UUs that you have in there, subtract that from 118, and those haven't been identified. Okay, so maybe we are closer to 113, somewhere in between 113 and 118. But then too, the book is fairly old too, like a couple years, and the data they used to put the book together were a couple years old, so it could be a few more than that. The number of protons is equal to the number of electrons in neutral atoms, uncharged atoms. So whatever the number of protons in that nucleus, you have to have that many electrons in that cloud around it for it to be neutral. Because protons have a +1 charge, electrons have a -1 charge. Neutrons, of course, have no charge at all. Okay. Now, there are different sizes of atoms that are still the same elements. How can that be? Well, what has no charge? Neutrons. So if you have different number of neutrons with the same number of protons, you have the same element, but with different sizes. So the same number of protons with different number of neutrons make up what we call isotopes. Iso means same, meaning it's the same element, but tope must mean something different too. Masses, weight, something like that. Now, the most obvious of these is the very lightest atom we have, which is that? Number 1 in the periodic table? Hydrogen. Hydrogen, the lightest gas there is. Okay? So let's go to hydrogen. Most hydrogen, just about all hydrogens, are a single proton with a single electron lying around. And that's all there is, folks. I mean, that's all there is. 1 proton, 1 electron, that's hydrogen. You can't get any smaller than that. Not at all. But occasionally, like maybe one time every 500 or 600, you'll find a hydrogen atom that has a single neutron as well. 1 proton makes it hydrogen, 1 electron to be electrically neutral, but 1 neutron is in there. And guess what you've done? You've basically doubled the mass of that hydrogen because hydrogen is so light. Okay? It's still hydrogen, but it's twice as heavy. Okay? And then maybe one time every 10 or 100,000 hydrogens, you'll find one with 2 neutrons. That's triple the mass of the most common ones. Okay? Now, this one they just call hydrogen. This one that has an extra or one neutron is called deuterium. Dew means three, twice, double the mass. And if you have two neutrons, you triple the mass. They call that tritium. Now, we may have in our bodies a couple of deuterium hydrogen atoms somewhere, and we may have a tritium somewhere in there. That doesn't make any difference at all. It's just hydrogen, okay, except it's more massive. But now when they list hydrogen, this is the symbol for hydrogen, H. Helium, it's He, so you don't get them confused, okay? Little e, okay? The number that's listed up to the upper left, that's the mass number. That would be 3, 2, or 1. The atomic number for hydrogen would just be 1, always 1. That's how many protons there are. If it's 1 here, it's hydrogen. If it's hydrogen, it's that 1 down here. The mass number, though, is how many, the total mass, which would be the number of protons and neutrons added together. Electrons don't have enough mass to even count, okay? Not enough to even bother with. But you only have 1 on here. But even if you had 115, it wouldn't be enough to count, okay? So don't worry about those. Okay, now, this is not in the text. I'll just tell you. What is the most common compound on the surface of the earth? You physical science. Most common compound on the surface of the earth. What covers most of the earth? Water, exactly. Oh, you said, I thought I heard something. My hearing's so bad. Okay, water. And you're drinking something right now, right? Now, water is all H2O, right? Now, oxygen, that one oxygen has a mass of 16. The two hydrogens have 1 each, usually, so that makes 18. Every now and then, if you have a deuterium in there, it'll be a 19, or tritium will actually be a 20. Now, that's enough of a percent difference that if you separate water with a centrifuge, very carefully do it, you can isolate a little bit of tritium that you might have and a little bit of deuterium you might have in those hydrogens. And that's called heavy water. Separate those out. Now, what those neutrons do, they help slow down fission reactions. So those tubes, have you seen on Star Trek or somewhere where they put the tubes in or out, controlling the nuclear reaction? Sometimes they're filled with neutrons. Sometimes that's heavy water. Now, every nuclear power plant in the country is built on a river or a lake or on the seashore. Has to have great quantities of water, mainly to keep it cool, because nuclear reactions produce an awful lot of heat, way more heat than you need. You also need it to make steam, so they need to have water. But the other things that are there anyway, they have these centrifuges running all the time, separating out deuterium and tritium, heavy water, because this heavy water has more neutrons in them, and that's what they put in the tubes that they use to control the nuclear reactions. Now that's a really simplified version. It's much more complicated than that, but that's where we use this. Okay. Now, getting back to atomic symbols and the masses, repeating what we just did. The mass number is basically, it's always the number of protons plus the number of neutrons. That's the mass number. The atomic number of protons only. That determines what element it is. Now, your atomic mass units, back when I was in school, hey, 100% attendance. All right. I went down to the cafeteria twice looking for you, but you must have already gone.
Yeah, I had to get some.
Huh?
I had left to get some meat.
Oh, I see. You were in the cafeteria, you know. But yeah, they had quit serving. Okay. All right, sorry. I missed you, but people kept coming in the office and I finally got away and you were gone. All right. By the way, since everybody's here, this will be maybe the last time I go over this till next time. Number one, student course evaluations have finally been open. So please do the student course evaluation. How do you get there? Look at your emails. Everybody able to access your emails, Boston State emails? Go to your emails, find the one that says student course evaluate, open it, you'll find the link, click on the link, you're there. Do it. It doesn't take long. Logan's already done his, didn't take long at all. Okay, please do the student course evaluation. Number 2, we just finished chapter 6 earlier today. That means we're going to have the test on chapter 6 on Thursday. Okay, we're in chapter 8 right now. That's what we're doing now. We're going to try to get at least halfway through chapter 8 tonight. And if we do, at some point, we'll probably quit. Okay? That means on Thursday, we'll continue in chapter 8, finish chapter 8, and then have the test on chapter 6. That's all we're going to do on Thursday. Okay? Then Tuesday, 4 things, maybe 5 are going to happen. Okay? 1, y'all are going to eat some pizza. Okay? We've had requested 2 cheese, 1 pepperoni, and 1 3-meat pizza. You have any preference? Those are okay? All right. So we're going to have pizza. And while y'all are eating pizza, I'm going to be returning every lab and every test that you've done. That means you've got to have them all in before Tuesday at 3:15. Okay? So you got today, tomorrow, Thursday, Friday, Monday, and Tuesday until 3, okay, to get things turned in. So please get them in. That includes research papers, right? Okay. So that's going to happen Tuesday of finals week, not next Tuesday, but next week, the one following. Okay? Then after you've eaten your pizzas, I've returned the papers, then we'll do the lab for chapter 8, because we would have finished that on Thursday, hopefully. And then we'll have the test on chapter 8, because we will have finished chapter 8 on Thursday. Okay, now, remember that one that kept flashing on and off? I'll give people the option, if you want to, you can go and take your final exam that day if there's time. And I think there will be. If you don't want to take it then, the final is not scheduled until the next Thursday, a week from this coming Thursday. That's when it's officially given. But since y'all are going to be here, we won't have enough to fill the whole time. If somebody needs to leave early, or people graduating and need to get the grades in early, I will give you the option of taking it early. You don't have to. I'll be here Thursday, and technically the final is 3 o'clock on Thursday until as long as you need to take. It won't take you more than half an hour. So if you can't get here until 3:15, no sweat. If you can't get here until 4 o'clock, I'm here till 8. So anytime Thursday. If you don't take it on Tuesday, take your final on Thursday. Okay? Then grades are due in, graduation is Friday of that week, not this coming Friday, the next one. Let me back up one thing. I said you can turn in stuff Friday. However, this Friday, when you could turn it in, I have a doctor's appointment at 9:20. So I'm going to be on the Birmingham campus from 8 to 8:40. And then I have to leave to go back to my doctor's appointment at 9:20. I don't know how long it's going to take. It's just an annual physical, but they do lots of stuff, okay? Do lots of tests and things like this. I don't know how long it's going to take. Usually no more than an hour. So let's say I get away from there at 10:20 or later. If I can get away from there before 11:30, I'll go back to the Birmingham campus and be there until 12. However, if it goes past, which I don't think it will, I'm not going back. So don't count on me being there any more beyond 8 to 8:40, and possibly catch me later. If I'm not there by 12 o'clock, turn the paper in here, because I'm not going back to the Birmingham campus until the last day. So don't turn it in there. Turn it in. Okay. That's the only fine ornament there. Okay. And grades I have to have your grades in by noon on the following Monday. So if you haven't gotten something to me by then, you're getting it incomplete. Okay? So please try to get everything in. If you get it in to me Monday, Tuesday, or Wednesday of that week after finals, I'll be here all 3 days. I can change the incomplete to a grade. They may have us in meetings, though, so I can't guarantee where I'm going to be. But try to slide it on my door if nothing else. All right. Sorry. It's the last time I have to say it because everyone's heard it. Okay. So, when you're measuring an atom, we call those atomic mass units. Back when I was growing up, they called them AMUs. Now they just call them U's. Okay, atomic mass unit. The symbol for that is U for unit. Okay. Because carbon-12 has 12 protons and neutrons, 6 protons, 6 neutrons, so a total of 12, that should have an atomic mass of 12. So they take carbon-12, take the 1/12 of that, and that's the carbon-12 isotope mass. And then all the others are measured based on that, because carbon's a very common atom in a lot of materials. Now, your atomic weight, okay, this is on the very small microscopic scale. Your atomic weight on the macroscopic scale is the atomic mass of an element averaged over the naturally occurring isotopes. Now, carbon is a naturally occurring, carbon-12 is a naturally occurring isotope of carbon. But there's also carbon-13 and carbon-14. I don't think there's a carbon-11. So the actual mass of carbon is not 12. It's 12.00 something or other. Let's see what it is exactly. 12.01. That's because there's a little bit of carbon-13 out there and just a tiny little amount of carbon-14. Now that carbon-14 is important though. Does anyone know why? Okay. In our atmosphere, somewhere way up there in the atmosphere is a band called the ionosphere. That's where the gamma rays from the earth, from the sun, are hitting that part of the atmosphere, knocking off electrons like crazy, forming ions, which are charged atoms. Okay? So that's why it's called the ionosphere. And it sometimes messes with the atoms that are up there. Now, some of the atoms up there are carbon dioxide, molecules up there are carbon dioxide. And it sometimes messes with those carbons and bumps them up to be carbon-14. You know, that's really high-powered stuff up there. Okay? So there is a certain percentage of carbon-14 in our whole atmosphere pretty much all the time. Now, carbon-14 is radioactive, but there's so little of it out there, it doesn't really basically hurt anybody because there's so little of it there. If it does damage the tissue, your body heals really quickly. It's only when you get massive amounts of radioactivity that's when the body can't keep up with the damage and you die, or you get cancer, or you get whatever. Okay, so the atmosphere always has pretty much a solid concentration of carbon-14. But because it's radioactive, it decays. But it decays really slowly. Like it loses about half of it, goes back to carbon-12, say every, I'm making up the number, 3,000 years. Okay. So, what is in every cell in every living object? Plants, animals, whatever. Carbon is in every element in the human body. I mean, every compound in the human body, in every cell. We're made out of carbon. We're carbon structures. Okay? And so is every plant and animal out there. So, if that plant or animal was living 10,000 years ago, okay, it had its concentration of carbon-14, but then it died. It went into the bottom of the ocean, or bottom of a swamp, or somewhere, and got buried. And over time, maybe it became a mineral. Okay, the bones became limestone, or something like that. So they go down and they dig up some of these fossils, and they study the amount of carbon-14 in it. And of course, it's been decaying. Half of it's decayed away to carbon-12 every 3,000 years, so they measure how much is there, and that tells them how old it is. Approximately, how old that is because the error bars are really big. Okay. So anyway, that is called, and you may have thought it was like Match.com, but it's not. It's called carbon dating. It's not one carbon dating another. It's measuring how much carbon-14 is there, and that's how they date how old fossils are. Okay? So it's by that measure of carbon-14. So there's always carbon-14 out there. Not very much, but it's easy to detect because it's radioactive. It's hard to detect other things, but radioactive, you can detect it by how much is there. It tells you how old. It does not have anything to do with this. It's just that's a different isotope of carbon-14. It's probably carbon-13 as well. So the atomic weight is the atomic mass averaged over all these different isotopes. But of course, carbon-12 being the most common, most of them are going to be 12, just occasionally a 13, and rarely a 14. So the average is just 12.01 because there's just not much of the other two out there. Okay. Now, back to the same slide we saw before. Hydrogen, 1 proton, so it has atomic number is 1, atomic mass is 1 because it has no neutrons. Deuterium, 1 proton because it's hydrogen, but 2 atomic mass because it has that 1 neutron. And because this one, tritium, has 2 neutrons, that's still 1 atomic number of protons makes it hydrogen, but 3 is the atomic mass. So you average the percentage of this, which is very much, most of this, and then a little bit of this, maybe 1 every 100 or 200 to 500, and then this one maybe 1 every 10,000, you'll see one of these. So you average those over the naturally occurring isotopes, and you come up with the atomic mass number for hydrogen, which is 1 point, see what it is in your periodic table, 1.008. So there's not very much of this at all. Maybe 8 every 1,000, okay? And this would be probably 1 every 100,000 or something like that. It's just really rare. And that's how you get that atomic mass, which is always a decimal number. The atomic number is always an integer because that's how many protons you have. Okay. So here's how we do nitrogen. Nitrogen has 2 natural isotopes. The most common is nitrogen-14. Okay, 99.63% of the nitrogen in this room is nitrogen-14. Okay? Nitrogen-15, how many neutrons are how many neutrons are in nitrogen-14? Nitrogen has atomic number of 7, atomic mass of 14. How many neutrons does it have? Easy to figure. The difference between those, which is 7. So most nitrogen has 7 neutrons. However, when you do run into one of these nitrogen-15s, it has 8 neutrons. Why, we don't know. It's still nitrogen, acts like nitrogen, feels like nitrogen, everything's like nitrogen. It just has 1 extra neutron. Okay? Its percentage is 37.37%. That means 4 out of every 1,000, approximately, is a nitrogen-15. So, I'm so sorry. This is the atomic mass of nitrogen-14. 14.0300307 atomic mass units, U. Times its percentage, 0.9963. And then you combine that with 0.0037, that's the percentage here, and this is 15.00011 is the atomic mass units in nitrogen-15. multiply those together, add the two together, and then that then gives you the atomic mass of nitrogen, which will be very close to that, but not quite. Atomic mass of nitrogen, 14.01. Okay, there's enough of this to bump this up, so it makes it 14.01. That's because you have some nitrogen 15 in there. Does that kind of make sense? It's messy math, but it's all pretty simple math. Okay. You won't have to do this. Just know how that's where those strange decimal numbers come from. Okay. Now, there's a case study on the top of page 210 about the discovery of the nucleus, and this is mostly, it goes back to J.J. Thomson, then Ernest Rutherford. It's what we've already talked about. Really nice to read those to fill in some of the gaps of what the book said. Okay. Now here the slide set doesn't quite match the book super well. So I'll go by the slides here, but I can't tell you exactly where this is in the book. It's right around page 210 or so. This is what we call our classical atoms. Okay? Yeah. Here was a problem. Predictions of the classical theory. Okay? We knew that electrons go around the nucleus. They're flying all around there. They say orbit, but they're not clearly defined orbits. They just sort of scatter all the way around. But they go around the nucleus. That's what we say. Now, because they're going around the nucleus, they're obviously changing their velocities. Because anytime you have curved motion, you have acceleration. You have centrifugal acceleration. We talked about that, right? So a curved path indicates an acceleration. Now this is classical physics here, okay? So anytime something is accelerating, accelerated charges radiate. They give off energy because they're accelerating. Or if they're giving off energy, that means they're losing energy. If they're losing energy, they're ultimately going to spiral down into the nucleus and crash. But we know that doesn't happen because atoms don't crash. They don't fail to exist. But the classical theory would say they did. So we got a problem, Houston. Okay? We know that atoms do exist. We know that the electrons do follow curved paths. Where are we faltering here? That's where a new theory was needed. Okay? And this new theory, now, before we get into quantum, I should have said this earlier. There is a great table in your text about what we were doing before, table 8.1, which shows good old hydrogen and deuterium here, and they show how you come up with the atomic weight of hydrogen. Beryllium has just the one, so it's the same as the mass of that one. And I said it had 4 and 4. It's actually 4 and 5. It has 5 neutrons. Nitrogen, we went through that one. That gave you the 14.0067, which rounds to 14.01. Oxygen actually has 3 isotopes. Oxygen 16 is the most common, 17 and 18, and they have different ones. So that's, but the strange thing is the 16 is a little bit lighter than 16. It's 15.99491. But there's so many of those, 99.7959%, that actually pulls the average oxygen down to 15.9994. Okay, so that's a little bizarre. Fluorine only has 1, so that's the same. So you can see all these. Neon has 3, and you can see where these atomic weights come from. So if you want to play around with them, that table would be helpful. All right. Now, part of your lab, I wish we had some other examples in hydrogen, but part of your lab when we do it next Tuesday is going to be determining how many protons, neutrons, and electrons are in a stable, balanced, electrically balanced atom. And you can do that by those atomic numbers and atomic masses. The difference between the atomic mass and the atomic number, that's the number of neutrons. The atomic number is the number of protons, and you have to have the same number of electrons as protons. So get used to doing those, and that table there will help you do that. Okay, so let's get back. Now we're moving into 8.2. Now again, the book and the slide set are not matching up super well. This is the quantum concept, which is under 8.2, that first subtopic. Now, back at the same time all that other stuff was happening, people were worried about how that discrepancy by curved path, meaning you're losing energy, atoms can't exist, but we know they do exist, okay? Max Planck, who was a really incredible German scientist, and there are right now several institutes in Germany named the Max Planck Institutes. They're like major research universities here in the U.S. They're called the Max Planck Institutes. I know a little bit about them from two completely different sources, but kind of intertwined. We have some very good German friends that live in Birmingham. We're actually the godparents for their son, who's a sophomore, junior in high school. Excellent soccer player. He may make the Olympics, maybe not. His first time, but soon. He's that good, okay? But anyway, Olaf, the guy, the parent, his father worked at Max Planck Institute in Northern Europe. And we visited at his parents' home, Hansbergen and Hilda's home, and they took us to Max Planck Institute. He had retired, but he showed us around something. Here, go into this stuff. So I knew about it that way, okay? And then it happened to be several years ago, 2008 or 9, somewhere around in there, really good Italian friends of ours, their son was born in the U.S., okay? Fabio, who was a classmate of my wife's in the doctoral program at UAB, Fabio, after he graduated, got a job in Boston for a pharmaceutical company, and he was working out when his son was born, Giacomo. And then they moved back to Italy. But he was born in the U.S., so he was a U.S. citizen. So, as time went on, Giacomo was a brilliant kid, just like his dad, doing quite well in school. And his parents wanted him to have an opportunity to go to school in Italy or in the U.S. Certainly could get into Italy with no problem. But they wanted him to have an opportunity to come to college in the U.S. as well. Since he was a U.S. citizen, I thought that had happened, but they were still living in Italy. Well, they had come over for a year somewhere there. We got to meet the kids. We really liked the kids. The two daughters were born in Italy, so they aren't U.S. citizens. But then, my wife Karen had meetings in Italy. Happened to be right at Thanksgiving week. So when I got through teaching, I went over and met her, and we went up to see Fabio and Rita and the kids for Thanksgiving that year. And they love Thanksgiving in the U.S. Of course, they don't celebrate it in Italy, so we celebrated it big time. And we got to meet the rest of the family. And Giacomo was in sophomore in high school, something like that. And he sort of entertained us when the parents were busy, and because they had to work and stuff, and we were on holiday. And he was just a great kid. You know, he put up with these old people and entertained us. His English was pretty good, you know. And we just got along so well. And that gave his parents the idea, well, maybe rather than sending him on some exchange program, let's see if we can send him back to Birmingham, and maybe he can live with Charles and Karen. And they asked us, and we said, sure. And sure enough, he came and did his senior year of high school at American High School, so he'd have a better chance of getting in at American University. And so he did that. But in Italy, they have 5 years of high school, so he went back to Italy and graduated there too. So anyway, and then he came back to the U.S. He got a full ride scholarship to the University of North Carolina. Take it. And he was so close to taking it, but then he got accepted at Harvard. And he was so enthralled with Harvard. He was born in Boston and felt like he had to go there. So he spent most of his parents' savings to go to Harvard. They don't give full ride scholarship at Harvard. So anyway, he came, did his 4 years at Harvard, graduated in physics, and went back to there, and now is completing his doctorate at the Max Planck Institute in Munich. Okay, not the same one where our friend's father worked, but at a different one. So anyway, we know about Max Planck Institute. He was a brilliant scientist. He introduced this idea that energy was quantized. The energy comes in little packets, that little packets all have the same amount of energy. Now you can have a spectrum of packets, so it seems like you have a spectrum of energy, but really energy is always quantized. And this is Planck's formula. E for energy is equal to H times F. Well, H is Planck's constant, that's the proportionality constant. Basically what Planck said, energy is proportional to the frequency. The higher the frequency, the higher the energy. And the constant proportionality is Planck's constant. And it's good across the board for any element whatsoever this works. And that constant is an incredibly small number, 6.63 times 10 to the minus 24. And then what are the units of that? Well, energy is in joules. Frequency is in per seconds. That's what frequency is, cycles per second. So it's per second. Cycle is not really a unit. So if you multiply per second by joules, you get joules second, and that's what H is measured as. An incredibly small number. And that's Planck's constant. I mean, Planck's constant, but that's basically Planck's formula. So whatever the frequency of the energy is, that's all the energy is related to that one frequency. And then you change the frequency, you get a different energy. Then this little known guy, Einstein, you may have heard of him, maybe not, okay, came along in 1905, and he then determined that light was made up of quantized photons of energy. And he, I think, introduced that term photon. And that's why, when I was explaining how fluorescent lights work, you see the electrons that are flying back and forth, because it's AC, and you got that ballast up there, which is a huge capacitor that builds up all these huge amount of charge. So they're flying past, and when they go past that phosphorescent material, they bump it up one energy level. That's a quantum, one energy level, and then when they pass, it falls back down, giving off a quantum of light. But it's happening so fast, you see constant light, but each one of those is a quantized photon. Okay, the higher the frequency of the photons, the more energetic the photons. Okay, and I don't know what that's supposed to be a picture of. I guess it's, I don't know, but it's a neat looking picture. Okay, they don't ever describe what it is in the book. So that's the quantum concept. Okay.
Wait, can you go back real quick?
Oh, sure, sorry. If I ever get going too fast, slow me down. Okay. Everybody got it? Okay. Now here's my goal right now, folks. We're at getting awfully close to 5:45, aren't we? Okay, so it's just about time to call roll. So I'll wait till 5:45 to call roll. And what I'd like to do is, if we can, make it to the periodic table. Or maybe electron configuration. That might be better. I don't know. Quit coughing. There's no coughing in this room. Okay. Okay. All right. Okay, you got this one. Before we hit atomic spectra, let's go on and mark the roll. Okay. Logan's still here. Isn't it really close to 5:45? Is it?
It's 5:43.
5:43. Yeah, we'll go and mark the roll. Okay. Jay is kind of here. Okay. Ethan's still here. Amanda's still here. Jonah's here. Patrick's here. Thomas is here. Latricia's here. Frank's still here. Mendez is still here. But we lost Mark. Diamond's still here. And Ryan is mostly here. Okay. So. Do you need a little break now? I'm figuring we're only going to do about 2 or 3 pages more, and we'll probably call it quits today. Want to go and wrap it up? Okay, let's do that. Okay, but if you need a break, we've been going at it a long time. Okay. Now, and again, this isn't following the book too well, but it is here. This part is kind of just stuck in here. So let's hit it. Something that we've noticed long before we knew why is that everything pretty much has a spectrum. Okay? It's called the atomic spectrum. So let's say you had pure helium and you energize it, it's going to give off a spectrum. You do pure carbon and energize it, it's going to give off a spectrum. If you have just a mass of lots of things, we sometimes call that black body radiation. Here you have close to a continuous radiation distribution because you have all these different materials in them and you can't identify the individual spectrum. Okay? Now, that continuous radiation distribution depends on the temperature of the radiating object. Okay? And the greater the temperature, of course, the higher the, just like we saw, E is equal to H nu, the higher the frequency can be. Now, these are characteristic of solids, liquids, and some of the densest of the gases. They usually are in this black body radiation, sort of a continuous radiation distribution. However, very light gases like hydrogen, helium, neon, argon, oxygen, some of those light gases, they emit at characteristic frequencies. Okay? You can actually see the individual lines separate from that continuous distribution. Now, these bullets aren't especially clear in what they're meaning. Diffuse matter, like a mixture of all sorts of stuff, will give you incandescent gases. Okay? Now these are gases that give off light when they heat, like these up here. Not necessarily heat, just have the energy of electrons flying by. those give off, they're incandescent. Okay. Now, hydrogen being the lightest of these gases, it gives off very distinct lines. And this is called the Balmer series. Now, this was discovered, identified, and studied, and actually very nicely done, okay, for hydrogen by a guy named Balmer long before we knew anything too much about quantum mechanics. And it's just really amazing how close he came to modeling this, okay? So here is basically what we have with a prism. If you have light here, now this is a regular incandescent light bulb, probably a tungsten filament, argon gas, whatever, and it's giving off light. You send that light through a little slit. Most of the light gets blocked, only a little bit goes into a narrow band, a slit, okay? It goes up and hits this prism at a certain angle, and because that light is made up of a variety of colors, the spectrum, it splits. The reds split. Okay, let me see if I get this right. I think the violets split more because they're higher energy, the reds split less, or vice versa, however that happens. But it shows the reds at the top, violets at the bottom. And of course, you know your spectrum, don't you? Red, orange, yellow, green, blue. There really isn't an indigo, and then violet. They put indigo in there because it is a color, and it fits in there, but that's so you can spell Roy, G, put indigo in there and get bit, okay? So it's not really there, but I mean, I'm sure the color indigo is somewhere in there, but so that's where you get the spectrum. Natural light from the sun follows that. Most of our artificial lights try to match the sun as closely as they can, so they're going to follow that too, because those are the energy levels of light being split, okay? So that's your black body radiation, you might say, a continuous spectrum. The colors sort of smear. You see the blues and the greens smear, the blues and the violets smear, you know, it's all just kind of in there. Now, if you have, this is supposed to represent, I think, a laser tube, which is very pure light. Now, some lasers are helium and some are others, but this is a very pure one, not a diffuse one. You send that through the slit, and then the individual spectral lines show up. Maybe there's no red, but there's an orange, no green or yellow, but there's a blue, and then a violet, and I don't know what that's supposed to be at the bottom, or whatever it is, a lighter color violet, I don't know. But this then would show the line spectrum. The first was just the continuous spectrum. This is more line spectrum. Now these are pretty thick lines here. In reality, they can be very, very narrow. Okay. All right. Anyone need this one a little longer? Okay. So here came Bohr. Okay. He was, see if I can find out where he was from. Seems like it wasn't Germany, but I may be wrong. All right. No German physicist. No. Where in the world is Bohr? Oh, I got off a page. I'm sorry. Yeah. Niels Bohr. Okay, sorry. When I was counting pages. So we're going a few more than a couple pages. Sorry about that. So do you need to take a break? We're probably going to be 15, 30 minutes more. You okay? All right. Sorry. Niels Bohr, a young Danish physicist who visited Rutherford's laboratory in 1812, really became interested in the questions about that solar system model of the atom. That the nucleus was there like the sun, and the electrons were flying around like the planets and the comets and things like that. He got really interested in that, and he tried to incorporate the quantum concept that Planck and Einstein had come up with and kind of tie them all together. And I'm sorry, I missed let's go back to Planck. Sorry. Let's go back to Planck's constant. Ooh. Okay, we don't have much room to write here. So let's do this. Example 8.1 and 8.2. Okay. Okay, we're going to write them here. What is the energy so we're looking for energy of a photon of red light with a frequency. So the frequency for red light is 4.60 times 10 to the 14 hertz. What would be the energy of that red light? Okay, how do we determine that? There's Planck's law. Okay, E is equal to HF, where H is Planck's constant, 6.63 times 10 to the minus 34 joule seconds. Okay, so let's do it. This is equal to HF, which is equal to Planck's constant was 6.63 times 10 to the minus 34 joule second. 6.63 times 10 to the minus 34 joule second. Multiply that by the frequency. 4.60 times 10 to the 14. Now what is a hertz? A hertz is a per second. That's it, just per second. Okay? Now if you got your calculators, okay, and especially for this Chapter 8 test, I said already on Chapter 6 test, a good idea to bring your calculator. But most of those are going to be pretty easy calculations. When you get to the Chapter 8 test, please bring your calculators. I can't remember if there's any problems on that, but if there are, you're going to need them. Okay? Well, you don't have to have them, but it's helpful. So let's do this. Remember how to do scientific notation? 6.63, then look for the key that says EE or EXP. One of those two keys, EE or EXP. 6.63, EE or EXP, and then you'll get a place to put the number, negative 34. Now, if your calculator has a minus sign in parentheses, that's the one you use. If it doesn't, all it has is a straight minus sign, but has a plus minus key somewhere, then what you do is 34, then hit the plus minus key. If you have the negative sign in parentheses, do that one first and then do 34. Times 4.60, you don't have to put the 0 if you don't want to, EE or EXP 14. And press equal. And you see what happens, the second here and the per second here cancel out, go away. And 6 times 4, it's going to be something between 25 and 30. What do you get? 3.05 times 10 to the what? Minus 19. And your sole remaining unit is joule. That's what we measure energy in. So that's the energy of the red line, red light that's at 10 to the 14 hertz. Okay? Now, example 8.2 is what is the energy of a photon of violet light with a frequency of 7.30. Well, again, E is equal to HF, okay, which is 6.63 times 10 to the minus 34 joule second times, now this is violet light, not violent, but violet, and that's 7.30 times 10 to the 14 hertz, which is per second. Okay? And again, the per second cancels with second. And we get this time something around 45 to 50, right? 4.84 times 10 to the minus 19, right? Minus 19 joules. Okay? Now, they're both pretty small numbers, but this is about 1 and 6 more than times that. Okay? So you see, the higher the frequency, the higher the energy. Not by a lot, because there's not much difference in the frequency, but there is significant difference. Okay? And that's why going through a prism, the light gets spread, because the difference in energy, one gets slowed down more than the other, and that's why you get the spectrum. All right. Now, sorry that I missed that. Oh, here was atomic spectrum. That's on page 211. So that's what we were just talking about on 211. And then here are the figures that were at the top of 212. Okay. The two figures there, top of page 212, figure 8.8. Okay. Now we move into the Balmer series. Okay? Now, 1885. This is before anything about quantum mechanics had been even discussed, talked about. All they knew was what they observed. They observed the spectrum, and there was a Swiss mathematics teacher, not a researcher, teacher, J.J. Balmer, was studying the regularity of the spacing of these hydrogen-line spectra, and he was able to develop an equation that fit all the visible lines. Now, he assigned some values for n, and the values for n, 3, 4, 5, and 6. He could only determine 4 distinguishable spectral lines. Okay? But he measured the distance, and he came up with this formula. How he did this is beyond me. He's a way better math teacher than I am, okay, to come up with this. 1 over lambda, which is the wavelength of the radiation, the waves, is equal to r. Now, we haven't talked about what r is. Don't worry about it yet. 1 over 2 squared minus 1 over n squared, where n takes on these values 3, 4, 5, and 6. It doesn't work with 1. It starts with 2 and goes up to 6. Okay? Now, r is a constant. It's another one of those proportionality constants. It's 1.097 times 10 to the 7th, and that's in per meter. Yeah. Per meter. When I first looked at that, I thought it was liters per meter, and I said, no, that can't be true. That's just 1 per meter. Okay. So I'll just put per meter so you don't get confused about what that is. Okay. Now, they don't give us what the name of that constant is. Let me see if I can find it. No, they don't give it in the front of the book either. There is one that's called Rydberg's constant, but that's not it. This is just the one he came up with. Just a constant, proportionality constant, to make everything fit. Now, with that in mind, then he came up with these. He observed 4 lines. They were violet, 2 violets, 1 blue-green, and 1 red. This was the red. Maybe I should put little r so you won't confuse it. This is red. This is blue-green. This is violet 1 and violet 2. Okay? Those are the 4 lines he was able to observe, and he was able to distinguish, calculate what their wavelengths were. Okay? Now, those 4 lines became known as the Balmer series. Other series were found later outside the visible part of the spectrum. The equations of the other series were different only by the values of n and the numbers in the denominator. So it's really amazing he came up with this. Absolutely no idea about quantum mechanics. And yet he came up with a formula that we're going to see works like a charm with quantum mechanics later. Pretty bright guy. In your book, they show there's some ultraviolet lines that you don't see. Then you hit the violet and the blue, green, and the red, and then you get infrared lines. Those you don't see, but they were able to distinguish them later. Okay? Now, what they asked us to do in example 8.3 was calculate the wavelength of the violet line, n equals 6, the second violet line in the hydrogen spectrum according to Balmer's equation. So that would be 1 over lambda is equal to 1.097 times 10 to the 7th per meter times 1 over 4. 2 squared is 4 minus 1 over 36. 6 squared is 36. Okay? See people, no, I thought I saw people punching away on calculators. Why don't somebody punch away on calculators? If you wanted to, make this a little easier. Make this least common denominator of 36, and this would be 9 minus 1, so it would be 8 over 36, which would be 4 over 18, which would be 2 over 9, so 2 ninths. So 1.097 EEEXP7 times 2 over 9. Anyone do that? It's 1.097 EE or EXP7 times 2 divided by 9. Okay? And once you do that, because this is a reciprocal here, find your reciprocal key. And we did this for when we were doing our parallel circuits, remember? Parallel resistances. It's the key that's either 1 over x or x to the minus 1. When you finally get an answer here, 1.97 EEEXP7 times 2 divided by 9. When you get that answer, then press one of these 2 keys, whichever key you can find, and that will give you the number. Has anyone done it yet? I see people trying. 4.11 times 10 to the minus 7. And that would be meters, because this is per meter. When you invert it, it becomes meter. There's your frequency of your wavelength of your violet line.
What does that symbol mean again?
The symbol, lambda, is the Greek letter, lowercase letter L. Lambda, it means wavelength. L length, lambda. Okay. And that's the wavelength of that violet line. This is number 6. And that's what the book got to. Okay. So now let's go to Bohr's theory. This is the bottom of page 212, moving over to 213. 3 rules for Bohr's theory. Electrons only exist in certain allowed orbits. Okay? And that's what I was saying before. Remember, there was an inner circle and an outer circle. The inner circle was one orbit, the next one was another. So electrons only exist in certain allowed orbits. Within an orbit, the electron does not radiate. Even though it's moving a curved path, it doesn't radiate. Okay? So that's the second thing. The radiation is emitted or absorbed only when it changes orbit. When it is emitted, when it drops in orbit, because it's giving up energy, it's absorbed when it jumps up in orbit. But they have to go up by orbits. And those orbits are fixed distance apart, so that's where you get your quantum of energy. The same thing that Einstein and Planck were talking about, quanta of energy. That's what happens. So here's the thing. If you have an electron here, it absorbs energy from somewhere, like the floating electrons there, jumps up in orbit, okay? But then the electron passes, it can't sustain itself there, it goes down in orbit, then you get one photon of a specific frequency that's determined by the difference of those two orbits. Like that n equals 6, that was the, we didn't get frequency, we got wavelength, but you can get it from it. That's how you do it. That is Bohr's theory. Okay. Now, here is it's explaining the same stuff in the Balmer series. Balmer series just was a mathematical model that made it fit. Here is the thing that actually describes it. The energy, okay, and this is in electron volts, is a measure of energy. If you think about it, remember what a volt was? Joules per coulomb. So energy per charge. So if you're down on the electron level, you're not measuring charge in coulombs, you're measuring in U's, atomic mass, just charge of electron, fundamental charge, in volts. But anyway, when it jumps down from, now the weird thing is all the energies are given as negative numbers to begin with. So when it goes down from a low negative number to a higher negative number, it's going actually increasing. Okay, so it's a bit bizarre. I'm sorry, I probably said that backwards. A negative number here going from a low negative number, a high negative number to a lower negative number, high negative to low negative, you're actually increasing the energy. Okay, and that's indeed what you do. Here is that 1 down there. Remember, 1 wasn't allowed. That's your minus 13.6, which shows up right here. Okay? But everything is falling down to the second level. Remember, 2 squared, and then 3 squared, 4 squared, 5 squared, and 6 squared. Going down to the second level. When it goes from this one to that one, they get the Balmer line in the orange category. This is in the blue-green category. This is one violet, and there's another violet. Okay? And those are the frequencies. We came up with lambda, that's the wavelength, but these are the frequencies. Okay? And most of this is an exercise in mathematics, calculating, but it's a fairly simple model. The photon energy, HF, that's the energy, is the difference between the high and the low. This is the high, this is the low. The difference there is what you get here. That's the difference between those two. And that gives you the Balmer lines. And that then determines these frequencies. Okay. If you want to play around with it, the numbers work. They're just sort of tedious to do. So the lowest energy state is called the ground state. Okay? You can't get any lower than that. There's still energy there, but you can't get any lower. Remember, originally when we said absolute zero, when we were talking about that in chapter 4, they originally thought that's where all motion stops. Now we know, no, it doesn't stop. It's the minimum energy level. There's still energy there, so there's still motion there, but that's as low as it can go. 2 is the one it's dropping down to, okay? These are the higher excited states. and falling down to this one. Okay? So the lowest energy is the ground state. I don't know whether they mean 1 or 2 here. They indicate sort of 2. The higher states are excited states, and the photon energy equals the difference in those state energies. These are in electron volts. These are in joules. Okay? Electron volts is usually what they use. Okay? The photon energy equals the difference in state energy. This is the hydrogen atom example. The energy levels, the line spectra. It works very nicely. Oh, isn't that great? Until they tried to go up to helium, just one more up. It got so complicated they couldn't do it. Okay. So this only works. The Balmer series, the Bohr's model only works for hydrogen. Sorry about that. It just gets way too complicated when you get more than one proton and one electron. The interactions just drive you crazy. Okay. So, the Bohr theory only modeled the line spectra for hydrogen. They could not get it to work for any other, but it worked like a charm there. Okay? Further experiments established a wave-particle duality of light and matter. Oh my goodness, what does that mean? Okay? And this was a guy named Young. He came up with a two-slit experiment that produced interference patterns for both photons, which is light, and electrons, which is matter. And he found out you could do it. You had to have different spacings and stuff, but they came out exactly the same. So basically, before they thought energy was energy, matter was matter. Now they found out they really act the same way. Light and energy do act the same way. They're just on different scales, way different scales, but they do act the same. So all particles, especially very small particles like electrons, act a lot like photons. And photons, because they're little packets of energy, they act a lot like particles. So that's why they call it the wave-particle duality of light and matter. It really gets fairly complicated. All you need to know is it's there. Okay? And Young's two-slit experiment is the one that showed this. Now, they don't really talk about who Young was. Trying to find if they mention any more about him than just his name. I don't see it. Okay. Now, where we are now is in 8.3 on page 215. Now, like I said before, waves and matter both have characteristics with each other. So we think of energy forming in waves, also matter has waves. And this French physicist Louis de Broglie, okay? Now, I can't ever say his name without thinking of my quantum mechanics professor at Georgia Tech. I actually had 2 courses on them. They're 2 of the worst things I ever suffered through in my life. He was very, very Irish, okay? And when he said this, I mean, it came out like he was gargling or something, you know. So I can't even come close to it. But Louis de Broglie, okay? French name pronounced by an Irishman, it was awful, okay? In 1923, so a bit after all these other guys, he postulated these matter waves, okay? Young had shown they existed. He postulated what they might be. The wavelength of the waves are related to the momentum because usually matter has mass and velocity, so that has momentum. The wavelength is related to that. And the matter waves in atoms are standing waves. Now, I don't know if you know what that means. Now, probably have asked this question before. Have any of you been to the Wayne Science Center? Okay. At one time, they had this wave machine going that made vibrations in this line, this wave. And what you could do is spray water droplets there, and then you'd see these standing waves. And it would look like it was just actually that thing was going very fast, but it was the strobe light and it was catching at just that, the frequencies. You can see that. That's what he says, standing waves. Okay, fixed at both ends and so many nodes in between. Okay? Now, here is de Broglie's relationship. Remember, momentum, mass times velocity. The wavelength is related to that by, guess what? Planck's constant. It keeps showing up in various places. It fits here like a charm. Planck didn't have a clue about matter waves when he came up with this, and yet here it shows up again. That is a universal constant. Planck first discovered it, but it's used in all sorts of places. Okay? This is de Broglie's formula. Okay? Now, here's what we mean by a standing wave. Okay. We say that the electron goes around an orbit. And this is the simple model. It just flows around an orbit. In reality, it doesn't. Electron is a little bit of mass. Remember, it does have some mass. Very little, but some. But it's a wave that does like this. But it's a standing wave, meaning everything's connected. And it keeps going like this and going like this and going like this. If you tried to change something in that, you would have something that disconnects here. That is a misfit. The orbit's still there, but if you try to set up a different frequency here, it's not going to work. It depends on that momentum and the relationship there. So this is what actually happens. This is what doesn't. This is why, going back to Planck, he said, as long as they stay in the orbit, there is no energy given off. There is no energy absorbed or given off because they're in a fixed standing wave. And everything's hunky-dory. It has its own frequency and everything else. So it just goes like that. Okay. Now, before we move to this, let's back up one and use the formula, 8.5. What is the wavelength associated with this is a really big particle here. So we're looking for the wavelength associated with a 0.150 kilogram baseball. Okay? With a velocity, so this is the mass of the baseball. The velocity of the baseball is 50 meters per second. That's a mass with a velocity. That's the momentum. Well, what would be the wavelength associated with that? De Broglie's formula here, 6.63 times 10 to the minus 34 joule seconds divided by 0.150 kilograms times 50.0 meters per second. Okay, before we go too much here, okay, this is a kilogram meter per second is why we measure momentum. But remember that also could be done as a Newton second. So we could call that a Newton second. Well, probably the easier thing is break the joule down. So let's do that. First, do the multiplication and division there. It's going to be an incredibly small number, right? 6.63 EE or EXP, negative 34, divided by 0.15, and then divide again by 50. Anyone got it? Or you could divide by open parentheses, 0.15 times 50, close parentheses equal, whatever, however you want to do that. What do you get?
Uh, 8.84
8.84 times 10 to the negative 35th meters. Now, where do we get meters? Well, let's see. A joule is a kilogram. And by the way, I forgot. I should have offered. I got some cough drops here. You want one? Okay. I haven't taken them either. Okay. That's a kilogram meter squared per second squared times second. So that's going to wipe out one of the seconds. And you're dividing it by a kilogram meter per second. Well, the kilograms are going to go out. One of the meters goes out, and the per second goes out. So you're left with meters. So that's where you get it, and that's a good unit for a wavelength. So there's the wavelength of the baseball. Lambda for the baseball is 8.84 times 10 to the minus 35 meters. Very, very short wavelength. Incredibly short wavelength, which means small wavelength. That's a 10 there. Okay. So the example 8.6 is what is the wavelength associated with an electron. So let's go, yuck. Okay. So we're going to change to the mass of electron. We'll have a velocity of the electron. Planck's constant stays the same. So these will change, and this will change. Okay, those units do, and of course this number is going to change big time. Okay, so what is the wavelength associated with an electron with a velocity of 6 times 10 to the 6? So the velocity here is 6.00 times 10 to the 6 meters per second. Much, much faster than even Jay's fastball. Okay, so, not listening, is he? Okay. We got to find the mass of electron. If you go to the front inside, hopefully somewhere you have near the front of your book, the electron rest mass, 9.11 times 10 to the minus 31 kilograms. 9.11 times 10 to the minus 31 kilograms. Really small mass, okay? So that's what we'll put down here, 9.11 times 10 to the minus 31 kilograms, and the velocity is 6.00 times 10 to the 6 meters per second. Punch those numbers in. You're going to come up with meters, so I left that alone. Anyone got a calculator to do it? 6.63 EE or EXP negative 34 divided first by 9.11 EE or EXP negative 31. Divide again by 6 EE or EXP 6. And what do you get? Anyone got it yet?
Uh,
1.21
10 to the minus 10.
10 to the minus 10 meters. 1.21 times 10 to the minus 10 meters. Guess what, folks? You will never be able to measure a wavelength that is as small as that baseball. 10 to the minus 35 meters? Are you kidding me? That is incredibly small. But that sounds like a small number here, 1.21 times 10 to the minus 10. that basically is a meter, well, 10 to the minus 3 meters is, do I have one? About the thickness of a dime. Okay. Do I have a dime? Don't seem to, but I have a penny. That will do. Okay. Saw it down there, but I don't. Okay. So take that. That would be 10 to the minus 3. Slice it into 1,000 little slices. Now that's awfully small, but that would be 10 to the minus 6. And then each one of those is 10 to the minus 3. So, yeah, it's still pretty small, but it is measurable with sophisticated equipment. So yeah, that's a much easier to measure, and it does come up with a wavelength. So that's matter waves. The new theory that does this, and by the way, let's go on to the next slide here. The wave mechanics, okay, were developed by a guy named Erwin Schrödinger. Remember, Bohr's model only worked for hydrogen. Schrödinger came up with a model that worked for just about anything. It treats the atoms as a three-dimensional system of waves. These waves that have to be, I want to say closed waves, standing waves, okay. Treats the atoms as three-dimensional systems of waves, contains successful ideas of the Bohr model for hydrogen, and much more. It goes way beyond hydrogen. It describes how the hydrogen atom and many electron atoms will work. Because you see, hydrogen only has one electron, easy to model. These are many electrons, you have to have all these waves in there. This forms our fundamental understanding of chemistry. That's where we'll pick up next time. How these wave mechanics contribute to our understanding of chemistry. Okay? And so we'll begin next time by the quantum mechanics model. Okay? And we'll talk about these various quantum numbers, and they're going to tie together to tell you how the periodic table is put together. It's going to be pretty exciting. I can tell y'all are fired up. Okay? Way to go. Okay. So we'll stop there. I'm cheating you out of some of your